Okay, okay. 1 minute. Yep. All right, I think we should get started. Okay, good morning. I'd like to welcome you today to the second of our keynotes for this federated conference. And it's my great pleasure to introduce to you this morning Cristina Cifuentes, who is the Vice President of the Oracle Software Assurance Organization, where she leads a team of security researchers and software and machine learning engineers to make application security and software assurance at scale a reality. She was the founding director of Oracle Labs Australia in 2010, where she led a team of researchers and engineers for close to 12 years, with a focus on scaling up program analysis techniques in new application security tools. Cristina led and successfully released Oracle Parfait, a static analysis tool that is used by thousands of C, C++, and Java developers every day. There's much to say about Cristina. I won't go through it all, but I'll just mention that she served on the executive committees of ACM SIGPlan and IEEE Reverse Engineering. She holds patents as part of her work at Oracle, and she also channels her interests into mentoring young programmers and minorities in STEM. And so it's my great pleasure to introduce to you Cristina Cifuentes.
Thank you. Thank you, Tony. And thank you, everyone, for being here this early. It's my pleasure to be with you today, to be able to talk to you about some of the work that we have been doing in Oracle and initially at Sun Microsystems for the past 18.5 years. So today, I'm going to focus on this tool called Oracle Parfait that we started developing back when I was at Sun Microsystems. The idea back then was to be able to develop a static code analysis tool that would find vulnerabilities in code. And when I started this work, we were working with the Solaris operating system. And when you looked at the ON operating system networking consolidation, it used to be 6 million lines of code back in 2007. And so we were dealing with millions of lines of code. And everyone was interested in being able to focus on precision and scalability because there were many tools that at the time were coming out in the market and they would take a lot of time to run. And given that you have millions of lines of code, as a development organization, you want to be able to see the results quickly because you cannot wait for 2 days or 1 week to be able to get the results. That was 2007. Now, today, we're working with a lot of cloud code, and now we're talking about billions of lines of code. So code keeps on growing, and if we extrapolate and we start thinking about the future, now with the LLMs being available that generate code for you, now we're talking about infinite code, right? And there's more and more code that becomes available, and we need to be able to help our development organizations be able to find not only the vulnerabilities, but also see what are they going to do with all of these vulnerabilities, which I'll talk to at the end of this talk. So today at Oracle, Parfait is being used by thousands of developers worldwide across many different organizations, including, like all of our enterprise code bases. We also have open source code bases, and of course, like all of the cloud services. And there's thousands of these cloud services that are running as well, Parfait. So my talk today is going to focus on three different topics. I'll start with the initial work, just give you a little bit of a summary as to some of the research that we focused on, and I'll point at some of the papers. Then I'll focus on the current work, and then we'll talk about exploration into the future. So with our initial work that started back in 2007, so during the first 10 years, we were basically focusing on how can we make a static analysis tool that finds bugs and vulnerabilities be precise and also scale up. And one of the things that we realized was that with various different types of bugs and vulnerabilities, some of the bugs are very localized, whereas others are non-localized. They rely on parameters that are passed through the method or procedure, and then you have to walk through like various different parts of the program in order to determine what the issue is. So that prompted us to realize that you don't need to be spending like all of your time using your most expensive analysis, because some vulnerabilities and bugs are going to be found with very simple analysis, whereas others will need that more expensive analysis. So in this architecture, we were focusing purely like on the C programs, because Solaris was written in C, of course, right? And we would start by finding what is the list of all of those potential locations where you may have a bug or a vulnerability, right? So if you think of buffer overflow, anywhere where you're doing a dereference, potentially you may have a buffer overflow at that location. So that's the list that we would construct here. And those are all potential defects. And we had various different analyses that go from very, very cheap and quick to more and more expensive to be able to sort out like bugs or defects that were found. And if it's a real defect, it would put it in a list. If it determines that it cannot be a defect, it would put it into another list. And anything else would be passed to the next analysis. And the other thing that we did with this architecture was to be able to have like this layered approach, but across different bug types, so we wouldn't be sharing necessarily the same analysis, so that allowed us to be able to scale and be more precise. Now, our actual implementation, like described in this paper at the bottom, from 2008, the actual implementation was built on top of the LLVM infrastructure. And as you know, like the LLVM infrastructure doesn't support the Java language, it doesn't support the PL/SQL language, but these were languages that were very important to Oracle. So as such, we ended up creating translators that would translate those languages into the bitcode LLVM intermediate representation that LLVM uses. And we use some of the metadata that you can store in the BC files to be able to store extra information for some of these languages. For example, like hierarchy information that gets stored in metadata. And then the analysis proper, like would take these files, this intermediate representation, and then it would run like the analysis proper Parfait to be able to determine any bugs, vulnerabilities, or defects in general. Now, a lot of the focus was, as I mentioned initially, on scalability, given that the code bases were already millions of lines of code. Development teams, when we talked to the Solaris organization, they wanted to be able to have a run that would work overnight. And for them, overnight meant that they needed to run various different tests that they would run every night, as well as the Parfait tests. So you really had a window of 2 hours at night to be able to run over like the 6 million lines of code. And 2 years later, that code base was actually 10 million lines of code. So you really needed analysis that would scale up really well. And what I'm showing here is data using a recent version of Parfait. So this is using the November 2025 version of Parfait. Now it's running over various different, with multiple cores, 16 cores, and a lot of RAM. But it gives you an idea of all the various different languages that we're supporting. And down here in these papers, there's description about the techniques per se that we were using. But as you can see, like with the analysis for code bases like C and C++, you can run the analysis proper, 193,000 lines of code per minute, right? That's really, really quick. It varies depending on language, right? Like for Go is 245,000 lines of code, for Java 289,000 lines of code, and so on. But the point is that you can run over millions of lines of code very quickly and be able to get answers. Of course, an analysis could always run fast and not tell you many useful issues. However, our focus, has been on how do we do that deep static code analysis? So how do we do interprocedural analysis? Because those vulnerabilities are the ones that really matter for the various different organizations, development organizations. So in this slide, I'm showing some data that is pretty old. This data is from 2011 to 2017. And I'm showing this data because like these days, all of these like different defects have been fixed, and therefore I couldn't show you a graph like this anymore. But this is data when we integrate it into one of our large organizations. The first part that you see here at the left is the initial baseline. So in June 2011, when Parfait ran over that code base, it generated a certain number of defects, right? Now you can see that over time, issues are being fixed. And then there's a new spike, and those new spikes were because we introduced like new analysis, and sometimes those new analyses were at the request of the actual organization. So in this particular spike that you see here, like the highest one, that was a specialized analysis that this organization asked us to introduce for them, because one day they came to us and they said, oh, from time to time we get this crash at customer sites, and can you do something about it? When they explained the issue, it was something that we could actually encode through static analysis. So we did the encoding. It ended up reporting potentially a lot of issues. And so the development organization had to decide how to fix the issues. And as you can see, like over a period of 1 year, issues went down, and collective things start going down and down to almost zero, right? So this is an example of one of the organizations that when they integrated Parfait, they integrated in what used to be called the nightly runs, right? And through these nightly runs, what they were doing was getting their release organization to determine when issues needed to be fixed. They didn't want to flood all of the development teams with, here you are, hundreds and hundreds of issues for you to fix. They would actually do it in stages. And then over time, like they go to like, there's almost any issues, right? They continue to run Parfait on a nightly basis. But let me show you before that, this little view. This view was a view that we used back then to be able to explain to the developer what was the issue. So what is like the trace witness, the path that takes you to the issue? In this particular case, it's an SQL injection. This SQL injection is listed here on line 108 on the right-hand side, bottom right-hand side. But as you can see, there are two different files, and the issue actually starts on this first file on the left-hand side. And we would tell you like there's some tainted data, it's being passed here, in this case it's being returned, it's being used here like in this next file. So now like the password becomes also tainted. Here password gets used as part of the query, so query becomes tainted, and then the query itself is, as a string is being passed to the SQL statement, and therefore that's why it's tainted, right? So this type of like trace witness usability was something that really helped the tool be able to help developers understand why the tool thought that an issue was an issue. So our work there up to that point was able to move, like static analysis from being a tool that was only being used by QA at testing time prior to release to being a time that was integrated at build time. And so developers now were seeing the results like on a daily basis. But even further than that, because the analysis, we were using this intermediate representation, and because the analysis were demand-driven analysis, so we would start on the particular issue, well, the potential location of where the issue would happen, say your buffer overflow at the reference, and then we would go backwards into the code to determine any dependencies, right, that were needed. So we're basically slicing the code. We're only looking at a small subset of the program. And so effectively, this allowed us to be able to do incremental analysis. And what's useful about the incremental analysis is, of course, that you're going to spend a lot less time. So let's assume that you have a code base that has n number of files. When we do the analysis with Parfait, we also generate function summaries for all of those files and each of the various different procedures and methods. So that means that later, let's say if Tony or Steve like submit like a new file, and this particular file depends on 3 other files, right? The analysis is going to take the summaries for the 3 other files along with the new file that was submitted and be able to do a full analysis over that subset of the code to be able to tell you these are the new defects that have been found. And so this type of incremental analysis, of course, is very quick, and it allows development organizations to be able to integrate now at commit time. And that's really what happened with several of our organizations at Oracle, that as developers make a commit or a pull request, depending on what particular system you're using, the tool actually runs. And if there are errors, like if there's a vulnerability or a defect being reported by the tool, the actual change doesn't go into the main trunk, and the developer needs to fix it before it gets deployed. So this data, also looking at all data from 2012 to 2018, shows at commit time the various different amounts of issues that were being found, and all of these become issues that get prevented from being introduced into the code base. So just with all of this work, right, like you're able now to move not only like from integrating at build time, but also now you're integrating into like the code base that the developers are using. And so this effectively changed the way that developers were operating, right? And all of these, like happened like prior to this whole movement about DevOps, but by the time DevOps came, it was already there. It was already working this way. And so it allowed new organizations like cloud organizations to really be able to start integrating their code bases. So as a summary, like our research was that big focus, scalability, precision, but also usability. Usability really helped in practice to be able to deploy the tools, and the precision helped so that developers normally see issues that are true positives rather than false positives. Now, today, now we're looking into automation, right? Because now we have larger code bases, you have thousands of cloud services running, and we have billions of lines of code. And when we talk to our Oracle Cloud Infrastructure team, OCI, They have thousands of projects. And their key requirement was that they needed to automatically onboard all of their OCI projects with minimal development effort. So that would be the success for the tool. And when they say like minimal effort from the developers, they really don't want their developers to have to be configuring for a tool. If there's something simple, yes, but they're not going to be changing each of their projects just because there's a new tool that needs to be integrated. And so for our integration, they have like a build service. And so we integrated into their build service. And in this integration in the build service, the build controller orchestrates the build, right? And you have like various different OKE pods that are going to run as one of the steps are going to do here, like the parfait run, right? And then when that run happens, it's going to send all of the results to a database where all of the defects get stored, including dynamic testing type of defects for this particular organization, right? What did we do to be able to have that automation? Now, the automatic onboarding was really focusing on configuration that was very simple to generate, right? Normally in the OCI build config, you have to specify what language you're using so that they know what compilers or what environment needs to be set up. If it's Java, you need to spell out like the JDK version that is being used. But also to be able to run our tool, we added like the security scanning service config. And that was basically spelling out build parameters that are needed in order to be able to run perfect. And I'm going to show you some data that was a summary of scans for 90 days. Like this particular automated service was first trialed out in March last year. And so this is data from November, right? Like figuring out like what should go into all of that configuration. You can see that depending on the type of build tool that is being used, there's different percentages of success of being able to run the tool fully automatically without any developer intervention. So out of the 19,000 unique OCI repositories that were scanned, in the order of 16,000 were scanned automatically without any developer intervention. And so this process we continue to develop because clearly it helps the organizations quite a bit. And the more automation that can happen, the better with cloud services. Now, the other thing that has been happening over time is the fact that our code bases now rely on a lot of third-party code, right? So the code base is not just the first-party code that you write, there's all of this third-party code that is out there. And everyone would be used to like a lot of the software supply chains that have been happening, software supply chain issues that have been happening over the years. I include here like two different examples. There's the log4j issue that happened, of course, in a December some years ago, where you had a CVSS issue of 10, so like the highest critical type of issue, and an attacker can actually control log messages with log4j, and other different attacks could be also done, right? There was also the PuTTY issue that even though it had a CVSS score of 5.9, with PuTTY, an attacker may compromise a victim's private keys. So these are significant issues. And these days, with the proliferation of the way how code is written, we end up finding ourselves with the first-party code is at the bottom, is a small percentage of the full code base that is going to be deployed. And the third-party code is quite large, depends on the different ecosystems that you're using. But more importantly, a lot of this code, there are known vulnerabilities, right, that have been reported in the National Vulnerability Database that NIST has, or other vulnerability databases that exist throughout the world. So this is data that can actually be collected. And so for this particular type of issues, third-party code, in this case, like, what is the key requirement for integration of a tool that finds third-party known issues? It's to automatically be able to process the software bill of materials, the SBOMs, that many organizations and many companies are generating to be able to detect those known vulnerabilities. And so I'll give you some graphs of our software composition analysis service. This particular first graph is looking at validation of the SBOM schema to be able to determine, like, at submission, during this 1 week, there were over 210,000 different SBOMs that were submitted. And then when you process them, you can see that depending on the day, it varies, like the load varies, right? And on average, if you take across like all of the different SBOMs and the runtime, the average processing time was 155 milliseconds. This is data like from September last year. So we're validating, like that the format is correct. In our case, we're using the Cyclone DX format, and we're also validating that the SBOM per se is well formed. Once that validation has happened, we also do integrity checks. And here with the integrity checks, you can see, I listed different pieces here. Okay, so the bottom one, it's hard to see. Okay, so we have like our P0s, and all the way up to here, we have our P99. But if you take like the average is 3 minutes and 3.37 minutes, right? So with this average, what we're saying is that there are some SBOMs that end up being quite large, as you can see, like from the chart. Like sometimes it takes a lot of time to be able to process them, and that's because some SBOMs actually have like many gigabytes of artifacts in size, and one needs to be able to download all of the artifacts to be able to do all of the hashes and be able to check that the integrity of the full SBOM is correct. And then once like the actual integrity checks have happened, then we can go and detect the actual vulnerabilities. Because these are known vulnerabilities, it's a simple match, it's a simple check that we have known vulnerabilities in a database, we have like this other code that came through, and you do the check. So this is really quick, 270 milliseconds or on average on this like 1 week in September of last year. So when you look at that, like across like a particular code base here, we looked at some cloud services, 130,000 SBOMs. You can see that because multiple cloud services are going to be able to rely on the same third-party code, you're going to find the same issue multiple times, right? So you do need to deduplicate all of these issues to be able to, at the end of the day, only ticket the deduplicated issues, right? Because clearly 1,300 issues is much better than 33,000 issues, right? Less development, less effort for the developers, and clearly, full information gets provided. Now, we also looked at some mobile code. Out of 21,000 SBOMs, we ended up with 48 findings, right? So this service, right, when you look at the DevOps model, is now integrating like that software composition analysis, both you can integrate at test time, you can integrate at build time, right? And with that, you have like a really good way of being able to get like the attack surface purely of your application, purely based on static analysis techniques. Of course, there are dynamic techniques that are complementary, but our focus today is purely on static on this talk. Now, let's look into the future. Now, with the development of all of these AI techniques and large language models and generative AI, right? Now there's this new neurosymbolic era where we're seeing like program analysis being combined with AI techniques to be able to do more, right? And one of the things that we have been focusing on, and this is purely exploratory research work, most of this has been done with interns, right, during the Australian summer. So every Australian summer in the past 3 years, well, this one, including this summer, the third one, has been full of fun just looking at what can we do in this space, right, and what works and what doesn't work, given that we have this large infrastructure. Now, last year, there was this report that came out from Veracode. And in this report, like they were actually looking into a lot of the generated code. And one of the things that they realized is that, of course, the code that is being generated also has like security vulnerabilities because it has been trained on code that has vulnerabilities, right? Now, this is significant because what people are finding is that in some cases, this generated code actually has more vulnerabilities than the code that the developers themselves write. In practice, in general, well, we need to deal with both types of code, right? Now, for us, given that we have this infrastructure, the Parfait static analysis infrastructure, our thought on being able to determine like how we could generate automatically patches for the defects or vulnerabilities that Parfait is reporting is as follows. You take all of the code, and because the tool is going to generate for you, here's the defect at line 2015, you have an SQL injection, blah, blah, blah. But it's also giving you that path, that trace witness that I mentioned earlier on, right? That particular path is actually giving you like path conditions. It's giving you a lot of context information as to why the tool believes that that's a particular issue, and you can traverse through that path. So if there's a fix, the fix is going to be somewhere along that path, right? Or the code around it. So for us, you know, like the idea is to not only feed like the particular defect, but also feed those path conditions, extra context into an LLM to be able to tell it like, let's generate patches for the code. And then the code that it generates, we then recompile. So we go and recompile it, rebuild it, rerun the tool, and be able to determine whether it's not reporting that same defect, or if it reports the same defect, then we run it again through this same process. So in practice, you know, like we started focusing on buffer overflows, right? We have lots of benchmarks on buffer overflows that we can use. So here's one particular example, and this in this example on the left-hand side, this actually comes from the OpenSolaris code base. It's the post-Daisy driver, and you can see here there are two different types of arrays, HTAP stop and VTAP stop. Both of them have been initialized with a constant size, and then there are different loops here for both of those arrays in both of these particular procedures. Now, when you look at the report that Parfait has generated, it tells you that there's a buffer overflow. It tells you that it's array dereference of HTAP stop sub I. The issue has to deal with the index I. And then it points you as to whereabouts in the code it is. The array size is 200, the index is 200, so clearly it's one of these OFY1 type of issues, right? Now, when we run our experiment, we end up generating these patches, and here, like, we're giving you like the diff, right, as to what was the original code, what is the new code that was generated. And as you can see, like, the generated code is actually computing what is like the correct size of the array, right? And it corrected for both arrays, the HTAP stop, the VTAP stop, in all possible locations where that happened. So this is one of those examples where the combination of the extra context that we provide along with the LLM, it generates correct patches for us, right? And when you rerun it, there's no such issue. I didn't include in here like a small table that we're starting to put together, because the technique, you think like we started with buffer overflow, but this is a generic technique. You have to test with interprocedural and also intraprocedural, right? Interprocedural, very good precision. Interprocedural, you need to start adding a certain type of context for the LLM not to get lost in the context that you're providing, right? And then you say, well, buffer overflow is not the only type of issue. So we started looking into other issues, and the technique generalizes pretty well across various different types of C defects, right? But of course, like everyone these days says, well, what about agents, right? Like, can an LLM agent automatically generate these patches rather than the way that we started doing it 2 years ago, right? And with that, what we're finding is that, of course, like you have to tell your agent, here's my prompt. In the prompt, we give it a task description. We generate the bug report. We store it into a file, right? And we tell it like what is the action that it needs to do with this report. And there's some like important notes that we tell it to take into account. And this has been critical in order for the agent to be able to generate like more reasonable patches for us. And you notice that this approach is different to the previous one in that here we're not providing the context. We're not providing explicitly the context, right? We're just saying, here's what the tool reported. Figure out what you want to do to generate correct code for it. But of course, we do need to have the bug descriptions here at the bottom, right? So if you're only processing buffer overflow, you would need a bug description here. If you're processing multiple different types of defects, you need to include them here so that when the agent reads this file, it can actually do something with it. And with this approach, what we're finding, here's an example of a XXC vulnerability in Apache Batik. And in this particular case, like we're looking at how would like a human actually fix this particular vulnerability, right? It's a simple patch here, one-line patch, and they're focusing here on ensuring that they're restricting this issue using DTD, right? Now, if you look at the way that the LLM generated the patch, this patch is correct, but this patch is stricter. It's actually more than what like the human would normally do. And so part of looking at this, like what would a human do compared to what is the code that is being generated, is to be able to understand like how good, what's the quality of the patches that are being generated. And you can see here that like in the third catch block, this one is actually looking at the load external DTD, which is the one that mirrors more closely like what a developer would actually do. Now, of course, you would say like this is a simple example. Could this type of technique work for complicated taint data? That's all under experimentation. We haven't finished the summer here in Australia. But of course, the reality is that you're all from the programming languages community. There's multiple different ways how you can generate patches, right? Being able to use augment program analysis context with LLMs is one way. It's very computationally expensive. Different way could be by having certain type of templates, especially for particular types of issues that are not that complicated to be fixed. A different way is relying on some of the program analysis techniques, since we know how to parse all of the code and so on. So there's multiple ways to do this, but at the moment, like for us, it has been mainly focusing on the exploration to be able to determine in which particular cases there would be value for us to rely on the computational power that the LLM requires to be able to provide results in areas that perhaps we couldn't do it in another way. And what about like all of that Gen AI auto-generated code? Well, it's the same. It's no different to any other code, so you can just pass it through the same type of techniques, where your patch generation could be one of many different types of patch generators. Okay, so then to conclude, so the main takeaways for us have been four, right? In order for us initially, so if we look at 10 years ago, 15 years ago, precision and scalability were really, really important in order to be able to have development organizations use the tool. For them, having not a lot of noise, as in not a lot of false positives, was key, because they want to be able to work on true positives, fix those issues. Usability was also very important in order to have that integration. And that usability has helped with automation. The more that you can automate, the more that the developer organizations are going to be happy. They don't have to do much at their end. Vulnerabilities and the reports are being sent to them. But now, as code bases keep on growing and there are more vulnerabilities also being generated, then the next stage that we're seeing is how to help the development organizations be able to fix these issues. So by focusing on looking into patch generation, we're looking into being able to provide the developer, here's the defect, and here's a potential patch or multiple different patches. You may want to send 2 or 3, depending on what techniques you're using, right? And then let the developer be able to determine if that's the correct fix for them. All right, and with that, I conclude today's talk. So with PPoPP, we have been able to do precise, scalable, and incremental static analysis for today's and tomorrow's code bases. Thank you.
Thank you, Christina. If there are questions, we do have a microphone here at the front. If you would like to come down and ask your question at the microphone, please.
Steve Blackburn, Google and ANU. Thank you, Christina. Great talk. This is such an interesting problem. Just let me start my question by just making sure I framed it correctly. So what we see is huge amounts of code that are generated by humans over decades, and then vulnerabilities that naturally arise, either first party or third party, and then tools that are able to scale to that extent that you've built that help us analyze this software, human-written software, for vulnerabilities. And then in the last part, you were talking about how you can use LLMs to help patch issues discovered by these tools operating on this essentially human-written code base. Okay, so that framing in place, I just wanted to ask 2 questions to get you to think about, or let you share your thoughts about where we're headed. 2 things. First of all, getting the LLM to actually find the vulnerabilities as well as fix the vulnerabilities. Because if I heard you right, this is about what you described as the fixes coming from the LLM. That's one part. The second part is the question about what happens when the code is increasingly written in the first instance by an LLM, and just perhaps, who knows, looks very different in shape and form and size and scale because the LLMs can generate code far more liberally, perhaps, than expensive software engineers, what that does to the problem.
Okay, so just one correction, so to speak, in that it's not the LLM on its own generating the fix, because we have tried that, and in general, it doesn't tend to work unless like the code happens to be code that is already well known out there, right? So you do need the extra context that the program analysis is providing in order to augment it with the LLM, right? So if we use that technique, then you were saying, what about if, in your first question?
Yeah, the first part was about getting the vulnerability found by the LLM rather than just fixed by the LLM.
Yeah, so we have done like a lot of different types of experiments where if you're trying to find like the vulnerabilities purely with the LLM without using like any program analysis techniques, we find that it doesn't do very well, right? And we have tried like also with dynamic techniques, like for example with fuzzers, you know, like people find various different types of issues. And when you try it with the LLM needs to be able to generate good seeds in the case of the fuzzer, right? And if it doesn't have context, it just doesn't know what to generate. So you end up with like a flat curve, right? Whereas if you provide extra information, and in our case, the information is coming through like the static analysis, then that extra information helps be able to generate better seeds to be able to guide the fuzzer, for example, as to where to go. So what we're finding at the moment is that we are always combining context from the program analysis techniques in order to help the LLM be able to generate something for us, like a fix or guide the fuzzer towards the right location and so on. Yeah. And your second question about like, if more and more code gets generated by AI and then the code ends up being looking like very different and so on, what's going to happen? Yeah, I guess, you know, at least, you know, at this point in time, the types of vulnerabilities tend to be the same ones. That's what we're seeing, right? Sure, like code could be more complex and so on, but that doesn't seem to be like much of an issue, like in general. If there are new types of vulnerabilities, then those ones would need to be integrated into the tool, of course.
Thank you, Christine. It's good to hear compilers are not dead yet.
Yeah, no, definitely.
Thank you for the great talk. Albert Cohen, Google DeepMind. Seems like only Googlers wants to ask questions today. I think it was really interesting to see your vision towards the infinite code type of issues. More specifically about concurrency bugs. Maybe they are not frequent, but they can be extremely nasty and hard to reproduce. So do you have a vision about how LLMs help with like reproducing bugs, Heisenberg bugs, etc.?
Ooh, no, concurrency is one of those areas that we haven't really looked into, like in any close detail, yeah. So no real thoughts, really. I should catch up with you afterwards.
So a similar context like Steve was presenting, you know, and he asked about the tool scalability. My question is more around, you know, also with the slop generated by AI, how do you see software maintenance and debuggability? Sometimes, you know, these tools are not going to be able to, and then what are you going to tell developers who need to go and debug this code by hand, if that's the case?
Oh, right, like if the developer needs to be debugging the generated code. Yeah, yeah, clearly it's much harder to do. Now, like what we're seeing, like we have generated some code, right? Like we had a project where we were trying to automatically generate the static analyzer through, you know, like final state machines. And the code that it generates is code that looks almost correct, but it's not correct. But also, the code doesn't compile in many cases, right? And so if code doesn't compile, then there was of course, you need to understand it in order to be able to fix it, right? And that helps. But like beyond that, if it's code that is going to be generated and just because it happens to compile, it's correct, so to speak, that will become an issue, yeah. And I think there are people in the software engineering community, they're doing studies like on this space because code understanding is becoming an issue, right? And for us, like when you look at code understanding, we start thinking more like about software understanding in general, and we go like, the truth is in the binary. The binary runs whatever is in your binary. We should be analyzing that, which is a little bit different from the developer view, of course, yeah, but that's where we are.
Thank you.
Hi, Christina. So I'm Madan Muswati from Microsoft Research. Great talk. Traditionally, there's an inherent trade-off between precision and so false positives and false negatives when it comes to static analysis, right? So, yeah. And in your 2 words in your title, precise and scalable, you actually hit a lot of work, hard work that went in order to make your tools do this trade-off correctly. So just wanted to know what's been your philosophy that worked in the past, and how do you make these static analysis tools make sure that the false positives are low while also the coverage of bugs is high, and how does that philosophy do you see is changing in the world of LLMs where it's not humans who are receiving the reports, but it's actually these agents who might have like more patience and so on?
Right. So initially, what we would do is take a code base and team up with one of the development teams, right? Like someone that knows that particular code base. And we would focus on a particular vulnerability that was important to different organizations so that we can look at code across different organizations because they look slightly different, right? And what we were always doing, and I remember, all of us developing like the analysis, and we would go, okay, today we're going to do testing. Let's say, assume it generated 200 issues. If there are 4 of us, divide the 200 issues into all of us, determine what false positive rate we're seeing, and compare, amongst ourselves. And that was really to be able to help tune the analysis as to what is working well, what's not working well. We were always aiming for a false positive rate of 10% or less before we could show the analysis to the engineering organization, right? So that was important for us. The other thing that was always important is to be able to have issues that were interprocedural, right? Because otherwise you end up with only focusing on the simpler issues, whereas interprocedural, those are the ones that developers are going to find like, oh, wow, look at these things, right? And so some of those examples actually came from development organizations, right? That if they have, like their code base for many years, they can give us like an older version of the code. Then we would know, like run through that and be able, like, do we find this type of issue? And if we don't find it, then it was like, what would it take the analysis to be able to find this type of issue? And so that's how, initially, like in that initial research era, we were focusing on doing all of these type of issues, like until we ended up with like that good confidence, right? Clearly the tool now is at a very different stage because it's now easier to plug in like new defect types just because the underlying infrastructure and the analysis have already gone through that process. Yeah.
Thank you.
Okay.
Hi, Michael Franz from UC Irvine. Great talk, thank you very much. So I found it very interesting that you're doing this analysis of third-party, your identification of third-party code with known vulnerabilities. And as we know, there is lots of third-party libraries that are not really properly maintained anymore. And I think there's a certain danger here that we're on a slippery slope, that people are going to use these automated tools specifically on third-party libraries that are no longer maintained by the original authors, even though we don't actually understand what that library does. So is it possible that you are actually kind of opening the door to saying, okay, if the original author doesn't respond, we'll just fix it ourselves and we'll use the LLM to do that?
Right. Good point, Michael. Yeah, and I think for us, okay, depends on the type of organization, right? Like different organizations have different rules as to how old a library should be, or number of maintainers, and all, different properties, right, that can be used. But for us, it's more like raising the awareness. Your code base is using this library A, B, and C that have known vulnerabilities in them, right? And so that's how we started, like that whole process. In the future, of course, like being able to fix the issue, yeah, like in order to fix like third-party code issues, yeah, people create forks, and there's all sorts of different ways to do it, right? Like if the library is being maintained, of course, like the developers may fix the issue, but if it's not maintained, sometimes forks get created, but many times the best way is you actually need to move on to some other library, right? Because if not properly maintained, like what is the purpose kind of thing, if there are issues, right, like in the library.
I just fear that this is going to, get people to say, oh, there's a quick fix. LLMs are going to fix it.
Oh my God. We don't know. Yeah. Thank you.
We have time for one more quick question.
Hi, Eyal Zaks from MobileHigh. So I feel bugs are an opportunity to learn from our mistakes, to understand something we failed when we developed the code.
Yeah.
In your experience, after finding the bugs and fixing them, has there been a way of feeding back to the developers some understanding of how can we improve so that we don't introduce these bugs in the first place?
Yes, so there are different approaches, right? Like there's secure coding standards in our company, and so development teams go through this like training process and so on. So that helps kind of like in re-emphasizing like, well, what to do about, like buffer overflow, SQL injection, cross-site scripting, like whatever it happens to be. But I think like something that we have noticed, like the developer gets like the issue, right? Like, and so they do learn from like, oh, okay, like I'm having this type of issue, and eventually I don't have as many of this type of issue. But what we see overall is that throughout the years, we still keep on seeing the same type of vulnerabilities, right? And so what you do have to couple that with organizations grow, and there's also change of staffing. Some people leave, new people join. We haven't done like proper study to be able to understand, right, like what is causing that. But at the end of the day, yeah, we still see that there's a lot of the same type of issues that keep on happening on different code bases. But having the tool there as a gate at least is helping with that, right? Be able to prevent those particular issues from being introduced into the code base.
Thank you.
Great question, thanks.
Okay, that's time now. I'll just like to ask you to join me, please, in thanking Christina for a very interesting, wonderful talk.
Thank you. Thank you, everyone.
And Christina's contact details are there if you want to follow up with any further questions you might have, so please do. Thank you.
And I'll be around the whole day today. Thank you.
Thank you, everybody, for being here on time. We're going to start the next session. Our first speaker is Gu Qiqi, and she will be talking about Spider, unleashing sparse tensor cores for stencil computations via strided computations.
Okay, good morning, everyone. I'm Qiqi Gu from Shanghai Jiao Tong University. Today, I'm excited to present our works, Spider Unleashing Sparse Tensor Cores for Stencil Computation via Strided Swapping. As many of us know, stencil computation is a cornerstone of high-performance computing. It is regarded as one of the 7 most important numerical methods for science and engineering, along with the linear algebra Monte Carlo method from Berkeley's view. And stencil is characterized by a fixed computation pattern involving neighboring input elements, conducting weighted sum and iterated updates. Common stencil pattern involves box and star shapes like this. And you can find stencil computation everywhere, from scientific simulation, numerical computing, and image processing. As shown in this figure, the convolution process is a representative box-shaped stencil computation. But whether it is a box-shaped or star-shaped stencil, the core challenge remains the same. How do we push the performance ceiling on modern hardwares? In recent years, we've seen a shift towards using tensor cores for extreme performance. It is a specialized ALU on modern GPUs designed for accelerating dense matrix multiply accumulate since the Volta architecture. However, there is a fundamental mismatch between matrix multiplication and stencil computation, specifically in the mismatch of tensor contraction. For matrix multiplication, it only contracts along a single dimension. But for stencil computation, it includes contractions along multiple dimensions. This mismatch makes it a challenge to adapt stencil computation onto tensor cores. Luckily, previous works have made great strides in mapping stencils onto tensor cores. Works like TC stencil, Conv stencil, and LoRa stencil adopt kernel flattening or decomposition strategy to align the stencil computation pattern with tensor cores matrix multiplication. But if you look at the transformed matrix in these methods, they all pad 0 values to construct a matrix. As a result, these solutions introduces redundant computation for these 0 values, wasting GPU cycles and powers. The opportunity to reduce this redundancy lies in the emergence of sparse ALUs. It is a kind of advanced feature of tensor cores, supporting sparse matrix multiplication of a sparse matrix and a dense matrix. GPU vendors like NVIDIA and AMD all introduces this new feature in their latest GPUs. These units can double the throughput by skipping the redundant operations on data that follows a 2-to-4 structure sparse pattern. That is to say, if we can make the stencil computation compatible with this 2-to-4 structure sparse pattern, stencil performance can be theoretically doubled. This arises the key challenge. How can we transform stencil computation into SPTC-compatible computation pattern? However, this is not a trivial task. We face 2 major challenges. The first is hardware alignment. The sparse format supported by SPTC has strict constraints. It requires the left-hand side operand have exactly 50% sparse ratio and fit with the 2-to-4 sparse pattern. The second is mathematically equivalence. Sparse tensor cores are designed for deep learning domain, engineers often adopt pruning or masking techniques to make model weights satisfying the structure sparse pattern. This may lead to computation variation, but is acceptable for large language models. However, scientific computing requires strict bitwise equivalence. We cannot simply zero out values to fit the hardware requirement and must transform the problem mathematically equivalent. In this paper, we propose SPIDER that solves the above challenges with 3 cooperative techniques: straddled swapping transformation for the stencil kernel transformation, zero-cost runtime row swapping for processing the dynamic inputs, and computing optimization for efficient execution. With all these techniques, SPIDER succeeds in unleashing the power of sparse tensor cores to accelerate stencil computation with strict mathematical equivalence guarantee. Next, let's look at the detail of these techniques. First of all, we need to map the computation pattern of stencil with tensor cores. The basic computation pattern of tensor core is matrix multiplication. It is also called GMM. We convert stencil computation into GMM using the strategy of kernel decomposition. It constructs the kernel matrix by decomposing the stencil kernel into independent vectors. For example, this is a vector of the decomposed stencil kernel. Next, this vector is replicated along the diagonal direction to make the kernel matrix like stairs. Then, matrix multiplication is conducted on this kernel matrix and the row input matrix, getting the partial output of this decomposed stencil kernel. Repeating the operation for all decomposed vectors and accumulating the output, we can get the final result. With this transformation, we get the kernel matrix of sparsity 2R plus 1 to 2R plus L. And if we set the parameter L to 2R plus 2, we can construct a kernel matrix with sparsity of exactly 50%, satisfying the sparse ratio requirement by the hardware specification. But a 50% sparse matrix isn't enough. It should also satisfy 2 to 4 structure sparse. Then we introduce our key technology, straddled swapping. It swaps the J's column with the J plus L's column for straddled columns. The index of the swapped column can be either odd or even. As shown in this figure, we perform the column swapping on odd columns. After this straddled swapping, we get a matrix satisfying the requirement of 2 to 4 structure sparsity. The last is encoding this matrix into the hardware-compatible format. It includes the compression of non-zero values and metadata extraction. After this transformation, the kernel matrix is succeeded in aligning with the hardware specification. During iteration updates in actual stencil computation, the stencil kernel is consistent, and this process introduced above can be done offline and incurs zero runtime overhead. However, the input is updated after each iteration. To maintain mathematical equivalence, it should follow the same swapping strategy as the kernel matrix. Then, the next question is how to reduce runtime overhead associating with this swapping. To resolve this concern, we introduce the next technique, zero-cost runtime row swapping. To be specific, the row swapping strategy is integrated with data index implicitly. Specifically, we modify the memory access offset calculation during the data movement from shared memory to registers, just adding an extra item into the offset computation process. And this term will be translated into a constant literal during compilation. As a result, this runtime row swapping incurs zero overhead during runtime. And our experiment validates this with no extra instructions and prolonged duration in the profiling. Finally, we apply typical optimization strategies onto computing kernel implementation. For example, we implement hierarchy tiling strategy optimization data movement across the GPU memory hierarchy, from the global memory to shared memory to registers, to maximize the data reuse. We also pack the metadata and compress the parameters to ensure coalesced memory access. Next, we evaluate Spider on an NVIDIA A100 GPU using CUDA 12.8. We compare it against industry standard libraries like cuDNN and academic SOTA works like ConfStencil and FlashFFT Stencil. The first is overall performance comparison. Spider consistently outperforms all baselines from 1D, 2D, and 3D stencil problems with different order configurations. Specifically, Spider is 4.71 times faster than the CUDA core-based method and 1.35 times faster than the best tensor core-based method. We also look at the scaling performance. Spider's performance scales gracefully as the problem size increases, reaches an average speedup of 1.86 times. Importantly, Spider consistently outperforms all baselines once the GPU resource is saturated. This proves that our strategic swapping is not just a theoretical trick, but a robust system optimization. Next, an ablation study reveals where the performance gain comes from. Merely aligning the sparsity to 50% gives us a 1.54 times performance boost. But a real jump comes from leveraging the sparse tensor cores, which adds another 1.66 times gain by eliminating half of the redundant workload. It is consistent with our assumption. And our final computing optimization adds an extra 4% to 12% on top of that. To conclude, Spider is the first system to successfully unleash sparse tensor cores for stencil computation. By transforming unresolved sparsity into an optimization opportunity, we succeed in extending the application of sparse tensor cores beyond deep learning into the general scientific computing. Our introduced strategic swapping strategy also gives a generalized transformation for sparse tensor core compatible operation. And Spider gives an elegant implementation for mathematical equivalent execution. Our code is open source and available on GPU. We invite you to try it out and help us extend this to even more computation patterns. And thank you. I'm very happy to take any questions.
We have time for questions. I have a question. It wasn't clear to me what are the constraints on the stencil kernel that you support. Like, can you support any size or any pattern, or is it specific to, you know?
It is a general solution to all stencil kernels. And by now, we support the box stencil. And this is the most general stencil pattern. All other stencil patterns can be adapted to the box-shaped stencils, and they can apply our method to accelerate.
Okay, well, very nice work. This is actually a question related to the chair. So I was wondering, have you evaluated, what is the order of the stencils that you have evaluated? Have you tried like high order stencil? And also you said that this is a general approach. Have you also tried with the stencil shape like cross? Because I see the box and I also see the star, but I didn't see you tried with the cross.
Not yet. We evaluate all the box and star stencil shaped, but if we want to try the cross stencil, maybe it is the same adaptation method.
Let's thank the speaker once again. So our next speaker is Jiaji Jiang, and he will be talking about ASM SPMM, which is unleashing the potential of ARM SME for sparse matrix multiplication acceleration.
Okay, hello everyone. I'm Jiaji Jiang, and today I will present ASM SPMM, and I'll work on accelerating general sparse matrix multiplication on ARM CPUs with SME matrix engine. SPMM is a critical and expensive kernel that appears across many domains, especially graph analytics and graph neural networks. Since SPMM often sits on the critical path, and improving it can lift performance for a broad class of applications. Modern ARM CPUs increasingly rely on matrix acceleration to deliver high throughput, and SME provides an outer-product-style matrix engine for dense computation. Since SME is now shipping in ARM version 9 products like Apple M4 and LS2, a natural question is, can we explore SME for SPMM, like many works on GPU 10 cores, despite its non-dense access patterns? For these questions, our investigation reveals several challenges. First, classic metrics like CSR are incompatible that prevents efficient SME feeding. Meanwhile, new formats like TCF or METCF were designed around the GPU tensor cores. They still retain inefficiency for SME, such as unnecessary intercolumn zeros and its strict block alignment assumptions. This does not match SME's execution model. Second, existing CPU SPMM kernels are largely vector unit-oriented, and GPU tensor core kernels usually is inner products based, and while SME favors outer products accumulation. Therefore, we need a kernel that matches SME's architectural strengths and also supports the practical optimizations required by sparse workloads. And third, even if SME is powerful and the traditional vector units on ARM CPU are still variable. For handling, for example, you can handling sparse fragments and doing works like preparation data. but SME and vector unit can also contain for cell matrix like registers, and so its performance depends on how we allocate work and scheduling instructions to keep both sides busy and without stepping on each other. And finally, sparsity is irregular, and ARM CPUs can be architecturally diverse across cores for different CPUs from different vendors. So traditional static partitioning policy based purely on non-zero elements counts often fail to generalize. We need more dynamic and hardware-aware load balancing policy that adapts at runtime and to adapt at runtime to different matrix structure and core capability. Given this challenge, ASM SPMM is designed as a full-stack approach. We co-designed storage formats and SME optimized kernel and matrix vector coordination and runtime scheduling for across different cores. It has 5 main components. First is SME-oriented format conversion for SME, and second is the dynamic task scaling across different cores, and SME optimized SPMM kernels. And finally is the matrix vector unit coordination component. And we also integration our design into GNN framework. First, our format, OPMC MCF, which solve for outer product memory compression format, is built for SME's outer products execution. It performs window current compression to remove empty currents and aggregates currents without rigid blocks constraints. And it uses mass multi-current merging with bitmap and predict spot to enable predict-driven execution. OPMCF reorganize sparse structure and so that SME can consume denser and more continuous micro panels. On the kernel side, we adopt an outer products oriented execution to match SME's accumulation style. Then we also add resource adaptive multi-tile concurrency to export available execution bandwidth. And finally, the structure computation is organized as a latency hiding pipelines, so data movement and compute overlap rather than serialized. Our goal is to reduce loss from memory and expose enough independent work to keep SME matrix engine busy. Another major practical improvement comes from a hybrid microkernel. SME handles most blocks, and while vector units process the most sparse leftovers, and we use a density threshold to select the path automatically, and we also applied interleave instruction scheduling. So vectors are size prefetching and preparation overlaps SME compute, but we account for cell resisting interactions, so we can overlap without creating too much destructive contentions. To scale across course, we use hardware-aware task mapping to assign an initial trunk tail to each course capability. Then do progress monitoring to detect imbalance, and finally applied work steering so ideal threads can grab the retaining log window cards from overloaded ones, and this keeps utilization high, and even when the sparsity patterns are screwed and all the hardware resources are as metrics. We evaluate our implementation on two represented platforms, Apple M4 and LS2, using 12 real-world metrics plus shield sparse metrics, which cover a broad sparsity range. We compare against baselines such as ARM Performance Library, M0, or Pyrmont. On the Apple M4 platform, ASM SPM delivers 3.5 to 7.9 speed out over other baselines, and this shows that with the right format and kernel structure, SME can provide large performance gains even for SPMM. Across the larger shield sparse set, we observe strong and portable speed outs on both LS2 and M4, and the key point here is portability. ASM SPMA is SME oriented and hardware aware. It transfers across different ARM CPU SME implications. Next, our study also shows that no single chip is enough. The full performance gains and benefit comes from combining formats, compression, SME optimized kernel structure, matrix vector coordination, and dynamic scheduling. This both our central claim. SME acceleration for SPMM is a co-designed problem and not a standalone kernel hack. On LS2, we get near linear scheduling, indicating that the scheduler and task decompose tasks well when SME resource scale with cost. On M4, its scaling is more limited due to the M4's cell SME units, which becomes the domain bottleneck. This is an important architectural reality and helps explain its cross-platform scaling difference. We also examined efficiency as matrix density increase, SME utilization rise, and about 5% to 17%, and energy efficiency improves roughly from 2.3 to 4.3 G-flows per watt. This aligns with the intuition that SME thrives when we can feed it with sufficiently compacted and compute dense work. And finally, we show the end-to-end impact on GNN inference, achieving 1.2 to 2.9 speed out. The gains correlates with how much of the pipeline is dominated by SPMM. We reinforce the practical relevance. Accelerating the kernel translates to meaningful application level improvements. Okay, thank you. Any questions?
Okay, good work and good talk. And I have a small question: is how expensive is the foaming conversion, and how does it pay off?
Oh, okay. Thank you. The conversion process is takes a little long time, but the conversion progress is usually offline, and it's a one-time course, and the matrix can be reused and in many scenarios, such as GNN inference or training. The format conversion is a one-time cost, and it can be averaged in its iterative work loss. So overall it's offline progress.
Thank you for the great presentation. My question about, you mentioned that you use SVE and SME at the same time, for different purposes. I just want to ask, can they work together well? And is there any constraint to use them concurrently?
Yes, they can theoretically they can be used at the same time for computation, but it can be we can achieve the effect that 1 + 1 equals 2. They can interfere with each other, and we can according to our application, and we cannot let them achieve 1 + 1 equals 2 effect. It can still interfere with each other. Thank you.
I had one question about the LX2 results that you showed for scaling. Am I correct in seeing that looks like it's not memory bandwidth bound, it's actually compute bound?
Yes, it is. SPMN is for GPU on GPU tensor core is maybe it's a bandwidth bound kernels, and but on a CPU, and if we only use the vector unit, or we do not utilize the SMB matrix engine, and it can still be improved by the SME engine. Especially we compared the sparsity, and this can leave this from the bandwidth bound to the compute bound side.
Thank you.
Okay, thank you.
Any other questions? Okay, let's thank the speaker one more time. Final speaker for the session is Yuchin Lee, and he will be talking about VDHA, vector-driven hash aggregation for sparse matrix, sparse vector multiplication on GPUs.
Sorry, how can I?
Okay. Good morning, everyone. I'm Yu Chenli from Tsinghua University. Today, I will present VDHA, vector-driven hash aggregation for sparse matrix sparse vector multiplication on GPUs. So our focus is vector-driven, the column major sparse M sparse V on GPUs, especially for weight sparse M sparse V. The key message is for column major sparse M sparse V, the read back stage is a bottleneck, and we can address it through a carefully designed shared memory hash aggregation together with a split and reorder to improve graph locality and compute memory pipelining. Here is our outline. First, I will introduce what sparse M sparse V is and the column major and the row major for sparse M sparse V. Then I will explain why readback is a bottleneck for sparse M sparse V and why existing solutions, atomic-based and sort-based solutions, are not ideal. So next, I will present our approach, VDHA, with three main components. The first is split and reorder to improve locality and balance work. Second is shared memory hash aggregation to merge update before write back. Final is compute memory pipelining to hide memory latency behind useful hash computation. Finally, I will show the result and ablation test, and final with a faster decision tree-based predictor to adaptive kernel. So sparse M, sparse V multiply a sparse matrix with a sparse vector and produce a denser result. We store the matrix in CSR or CSCs. So to design an efficient GPU kernel, there are three concepts to keep in mind. First is memory collapsing. GPUs read access memory continually within a warp. So a single transaction performs continual memory access. We want the threads in a warp to touch nearby memory, so it will be more efficient. Second is occupancy. Higher occupancy means more active warps per SM, which helps to hide memory latency. Third is memory stall. If a warp is stalled by global memory latency, it will waiting, so it will reduce the efficient. So our design aims to keep memory collapsing, keep occupancy reasonable, and reduce memory stall. For the application for sparse M, sparse V, it usually appears in graph analysis like BFS or personal PageRank, and also in machine learning, specking neural network, and scientific computing. So now sparse M, sparse V on GPUs typically has two types. First is row major, also called matrix-driven sparse M, sparse V. Here, matrix is stored in row major, the CSR format. We parallel over rows, and so a thread or warps compute over rows and parallel to produce output entries in result vector. We can view this as mask, sparse MV. Compared to sparse MV, we add an input mask to exploit sparsity in vector. If the vector mask is 0, we can skip some work and reduce memory waste. For BFS-like case, there is also an output mask. We can use the output mask to reduce duplicate update in result, since BFS output are often binary. However, this output mask is not general applicable to weight sparse M, sparse V, because we need to deal every update. So the key limitation is, even with the mask, row major sparse M, sparse V still tend to scan all rows of matrix, so it cannot fully use the sparsity of both matrix and vector. The second style is column major, also called vector-driven. Here, matrix is stored in CC. We parallel over non-zero of input in the vector. For each non-zero, we travel the corresponding column and generate contribution like vector dot matrix terms and scatter them to output entries. So this is a push style update, and it's naturally avoid unnecessary work because we only visit the useful non-zero of vector. But the column major introduces a critical issue, which is read-back conflict. Many updates may target the same position and will cause a data race. So we need to solve the data race. Typical approach use either atomic-based method or sort-based method. So we will briefly introduce why we based on column major, the vector-driven. That is because the vector-driven has a higher potential to exploit sparsity. In row major sets R travel, we walk, as we talked before, we will walk in the matrix to travel all rows and load column index first. Even with the input mask, we cannot avoid reading the index and checking the mask. So sparsity helps only partially. In contrast, column major CC travel is driven by non-zero in vector. We iterate only the non-zero of useful in vector and travel selected column. So we assess most necessary entries and without waste work. Therefore, for weight sparse M, sparse V, column major can better exploit the sparsity of both column and vector. The profiling shows a clear bottleneck in the read-back stage. A column major generates scatter cell update to result. This causes two difficult. First is it will cause conflict. Many updates may target the same result potential, which will need a data race solution. Second is the scatter style updates are not coalescing, which will harm the global memory output. So in practice, the read-back stage can take about 30% to 40% of total time. So optimizing read-back stage is very critical. So as we talked before, there are two approaches, which is atomic-based or sort-based. The atomic-based read-back directly atomic as the intermediate update to result. It is simple, but atomic become expensive under contention. So read-back are still scattered, so we paid both atomic cost and got a uncoalesced memory access pattern. It's not very efficient. Second is sort-based aggregation. This method stores intermediate updates, the key value pairs, in the buffer and sorts them by key, finally reduce the result. The reduced stage becomes efficient, but the global sort is very costly. So it adds an extra memory traffic and often not paid off. So this is our motivation. Hash aggregation as a third option. In sparse gem, shared memory hash tables are often used to merge intermediate updates to reduce global atomics. The idea is within one SM, we maintain a hash table of key value pair, merge the duplicate and flash unique pair to global memory. But sparse M, sparse V is fundamentally different. In sparse gem, the output is naturally partitioned by row. Each row accumulate is independent, so a hash table fits the row-wise workspace model. But in sparse M, sparse V, the result is a single dense vector. Updates are no natural partition, so a naive hash table cannot eliminate all conflict, and we cannot tolerate that huge memory table in shared memory. So the key question is, how can we design hashing so that most conflicts become local, and we can locally use hash table to aggregate the update? Our key idea is to create locality in each SM. Each SM handle only a subset of row at a time. By exploiting graph locality, most conflicts become local and can be merged in a small shared memory hash table. That is the motivation behind our approach. Here is our overall design with 3 components. First is split and reorder. We decompose a long column into segments and reorder them to improve locality and balance work. Second, we use a shared memory hash table to aggregate update, and finally flash to result. Third is compute memory pipelining. We overlap global load and hash update, which had a hash computation cost into the load latency. So next we will go to the 3 components one by one. The first is split and reorder. We do this because long column cause 2 issues. First, column lengths are highly skewed, causing load imbalance across SM. Second is within a long column, row indexes will not overlap, so the conflicts are limited and hashing cannot be useful. So we split long column into shorter segments and reorder segments by their starting position. And this makes the nearby segment become more likely to touch nearby, increasing the locality. And the cost is small because we only sort the segment IDs, not the whole matrix. Second is the main design of the shared memory hash aggregation, which in each SM we maintain a shared memory hash table, which is the key is a row index, and the value is accumulated sum. We use atomic compare and swap to and linear probing for correctness, and this is correct, and we use a fallback stage to avoid long tail stalls under heavy collection. We also designed the hash function to preserve low bit pattern as much as possible, so that indexes are close in matrix are still close to each other in the final hash table, which means we can flash the result to result more coalescing. And final is the compute memory pipelining. Even with the hashing, vector-driven sparse M, sparse V still suffer from irregular memory stall, so which cause frequently stalls. Hash computation also has non-trivial cost, and we can use the memory latency to hide the cost of hash computing. So we use a acyclic memory copy from global to shared memory, and in the acyclic copy, we will compute hash index and accumulate them. By overlapping fetch and compute, we convert stall cycle into useful work and efficiently had significant potent cost of hash computing. Finally, we will talk about our result. This shows our experimental result. We evaluate on 2 data sets group. First is pseudo-sparse for scientific graph, and second is connect and law for web and social graph. Each graph has at least 5 million non-zero. We test vector sparsity at 1%, 5%, 10%, and 20%. Test on NVIDIA A100. Over speed up, our baseline is 7. First is sparse MV. 4 column measured sparse M, sparse V, and 2 row measured sparse M, sparse V. We report across the best of 7 baselines, shows that we gained 1.41 times geometry speed up on connect and law, and 1.13 geometry speed up on pseudo-sparse. We also do an ablation test and sensitive test. ablation test showed why each component matters. With split, we improve load balance, and with reorder, we improve locality and hash reuse. Also, we do a parameter sensitive test. The best parameters are hash entries at 2048 and the thread blocks at 256. This is because this param balancing occupancy and hash collection rate. Final is our fast predictor. This is also important. Since there isn't one best method can fit every matrix, so adaptive selection is important. Our approach also is not best for every matrix, especially the diagonal-like matrix. Our hashing and reorder have less for diagonal-like matrix, so we built a fast decision tree predictor using this file matrix. It achieves 91.3% correctness on FE score and enable adaptive fallback. On silksparse, if we fall back to a default approach, our improves geometry from 1.13 to 1.16 and to 1.22 speed up with a stronger fallback. This is our reference. Thank you. I'm happy to take questions.
We have time for some questions. Can you go back to your evaluation slide? I just had some kind of dumb questions about your evaluation.
Evaluation?
Yes. So in this setting, are your vectors uniformly randomly sparse?
Yes, the vector is randomly selected and at the full sparsity.
I see. I think the other common case is often one non-zero in your vector. So I was curious if you looked at how performance goes as you increase sparsity, or I guess reduce sparsity in your case, like when it's very, very, very sparse.
Yeah. We test for sparsity from 0.1% to 20%. Across this sparsity, our approach is more efficient. And if the vector become more dense, the row major sparse M sparse V is more efficient. And when the vector become even more dense, maybe we should directly use sparse MV instead of sparse M sparse V. And our approach is efficient on lower sparsity or lower medium sparsity.
Thank you. Hash-based SPM is interesting. I just have a small question about this method. Can this be easily to port to other architecture, like SME-based CPU like this, or other like AMD GPU like this? Thank you.
Yeah, very good question. I think it can be also approach in AMD GPU, but in CPU, maybe the hash-based is not optimal since the cache in CPU is very strong than GPU, and the hash is to improve locality and another style of cache. So maybe in, but it has additional cost. So maybe in CPU, the hash benefit will be less, and the cost cannot be ignored. But in AMD GPU, I think it will work.
Okay, let's thank the speaker once again. And now we have a break until 11:30 a.m.
Okay, I think we're going to get started. So my name is Ruslan Nikolaev. I'm an assistant professor from Penn State. I'm going to be a session chair for cloud, for cloud and storage computing. So, so our first speaker is. Let me introduce the first speaker. This is. Xiao, I'm sorry if I, mispronounce the name. Xiao Kan Hu.
Yeah, sorry.
Is everything okay?
Hello, everyone. My name is Xiaokang Hu from Alibaba Cloud. Thank you for joining me. I'm thrilled to present our work, CatchMan, a comprehensive last-level cache management system for multi-tenant clouds. Let's start with the motivation, a fundamental resource challenge in the modern cloud. As you know, CPU and memory can be allocated exclusively to the virtual machines. However, the last level cache remains still be shared by the multi-node virtual machines on the same socket. This may lead to uncontrolled LLC computation and severe performance interference. For example, workload latency may be degraded by 2 times or even more. Especially in the cloud, we face the following cloud-specific challenges for the LLC computation. The first is the black box TNet workloads, which means these workloads are unpredictable and they are diverse. Second, the host-side metrics usually poorly reflect guest performance due to unlowing TNet objects for optimization, misleading correlations, and potential adversary manipulation. The second, cloud service providers honor service-level agreements, notably SLAs. SLAs demand fairness guarantee, not just aggregate throughput. Given the above challenges, we ask, does existing systems can solve them? The answer is no. For most prior systems, including cloud and non-cloud, like K-part, OL-part, or OBIG, they require application profiling, which means they are not suitable for the black box TNet workloads. There are some cloud cluster-level scheduling strategies like cache slicer for VM placement. However, it may lead to gaming risk. TNets may make false declarations to declare their workloads is cache sensitive to grab more resource. Other strategy like virtual machine migration, they are slow in minutes, and they introduce new overhead and probably service downtime. For hardware technologies like Intel CAT, they can provide static partitioning. However, they only provide chorus-grained control, and the number of cores is 4 to 16 on different machines. There are still unfairness for small-sized virtual machines, and likely lead to underutilization when the virtual machines go idle. So what we need is a node-level system to ensure fairness and no profiling. no assumptions for workload, and it can work in real time. To guide our design, we analyzed the millions of virtual machines over 2 years at Alibaba Cloud, and we have the following key observations. The first one is the ALC occupancy. It is the best fairness indicator as it measures the real-time cache usage of those virtual machines. Second, what Tina expects is a fair baseline, which is proportional to their virtual machine size. The third, perhaps surprisingly, excessive cache is not always good. For distributed applications, the temporary cache overuse may harm their performance consistency and disrupt the load balancing and result in long-tail latency. And the last one, virtual machine migration, which has been used widely in Alibaba Cloud, but migration only is not enough because it works in minutes. However, the workload usually changes in seconds. So we present CatchMan. It is designed to achieve the following 4 goals simultaneously. First, fairness with SLA guarantee. We ensure each virtual machine can get their fair cache baseline. Second, utilization efficiency. We want to minimize the idle cache lines. Third is the performance consistency. If a tenant wants performance consistency for their distributed applications, we enforce outbound for them. And the final is the real-time responsiveness. We want to adapt within seconds to the workload shifts. The key innovation is the gradient-based sharing mechanism. Although the hardware-assist class of service, which defines a subset of ALC ways a class can use, the number is only 4 to 16. However, we redefine them to a gradient hierarchy. Like in the figure, the clause 0 has full access to all ALC ways. The clause 1 has slightly less, and clause 2 has more less. Agents in the clause differ by a small block of ways, and they form different separation levels for the virtual machines. Then CatchMan can move virtual machines into agents in the clause to achieve smooth allocation adjustment, which means no aberrant jumps on the available ALC ways. And more importantly, this kind of sharing can enable high utilization because all of the virtual machines can be put into a lower separation level to use more cache lines. And at the same time, it can enforce effective separation for aggressive virtual machines by putting them into a higher separation level. To cooperate with the gradient sharing, we define different ALC states by measuring their real-time ALC occupancy. Like the left figure, a poor VM means its ALC occupancy is below the baseline and it needs help. Adequate means near baseline and it's all good. Excess means over baseline and it's a candidate for separation to free up cache spaces. The overflow means the TNet has a consistency requirement and we must separation is cache use to guarantee the performance consistency. A virtual machine, if it's idle, we classify it into the other virtual machine and put it in the default clause 0. Then if it has a load, it can immediately access all the cache space. And the virtual machine states can have transitions dynamically. For example, a higher contention or a lower contention, and catchman responds by do the suppression or desuppression of the catch to make the transitions. The real-time allocation algorithm is conducted by the catchman per cycle within seconds. In each cycle, catchman first classifies virtual machines into different ALC states. And if a poor VM exists, it enters into the phase 1 for fairness. It will pick some candidate from the excess to do suppression operations to free up cache space. If no pool, but there is some overflow, there are some overflow virtual machines, it enters into the phase 2 for consistency. It enforces upper bounds via suppression to meet the requirements of the tenants. And if no pool and no overflow, then the catchman enters into the phase 3 for optimization to redistribute excess cache lines among all the virtual machines. It can be based on fairness or performance first. Importantly, catchman adjusts only one or few virtual machines per cycle to ensure stable convergency, because one adjustment can have influence on all the ALC states of the machine, virtual machines. Let's see the evaluation. We put 5 virtual machines with different benchmarks. These benchmarks have different cache behaviors. We put them in the one socket to evaluate the fairness. For the left figure is the default free computation. We can see that the weak virtual machines with GCCR are starved. And it has chronic armed allocation. In the right figure, when we deploy catchman, it measures the ALC occupancy of all virtual machines and react on like T1, T2, T3 to do some suppression and desuppression to ensure that all virtual machines can meet their fair baseline. Then the next is the efficiency. We compare catchman with exclusive partitioning. An example is for 5 virtual machines, the close 0 is occupied by a virtual machine 1, 32 core, and the close 1 is occupied by 2, and the close 2 is occupied by the virtual machine 3. However, the last close 3 is shared by the small virtual machine 4 and 5. This kind of sharing still have internal interference, like the below figure shows. The virtual machine 5 is under allocation, and its real-time ALC occupancy is under the baseline for a long time. And moreover, if the virtual machine 2 is idle, but it holds reserved space, and it can lead to wasted cache lines. In contrast, when we deploy catchman, it first prevents starvation. The virtual machine 5 can get more cache space, and it can reclaim idle cache lines from the virtual machine 2 to increase the utilization. So compared to the static or exclusive partitioning, catchman has higher utilization and better fairness. This is the evaluation of the smoothness of our gradient sharing. We give an example of non-gradient sharing from the class 5 to 6. It has a significant jump of the available ALC ways. When we move a virtual machine, like virtual machine 2, from class 2 to class 6, the non-gradient sharing has aberrant drops of the ALC occupancy, and catchman can provide smooth adjustment and avoid such aberrant drops. This is the responsiveness and consistency. With Catchman, it can recover from load surge within seconds, and it ensures that upper bounds of the TNet negotiated upper bounds can be enforced by limits the ALC spikes during VM churn, such as the starting and stopping of virtual machines. We also evaluate our Catchman in the production, and we deployed it on over 200,000 servers. The left finger is the default free commutation over 72 hours timeline, and we measure the number of virtual machines with different ALC deviation ratio. We can see that thousands of virtual machines per hour suffered severe under-allocation, and the deviation ratio is over 0.2. After we deploying the Catchman, over 98% reduction can be achieved in the ASLA violations. The remaining 2% violation can be helped by the class level scheduling as a fallback mechanism. To conclude, Catchman is a practical, comprehensive ALC manager for multi-tenant clouds. It has the following key innovations. The first is the gradient sharing based on existing clause partitioning. The second, it has no node-level speed and no profiling of applications and no assumptions of the workloads. Third, it has real-time fairness enforcement via dynamic cache separation and deseparation by moving virtual machines between agents and clauses. And finally, it achieves high utilization while supporting performance consistency. Thank you. I'm happy to answer any questions.
So I guess we have time for maybe one question. Anyone would like to ask a question? Oh, okay.
Thank you. Very nice talk. I'm Yang Hongmei from Huawei. I want to ask how to determine the details of a virtual machine and how to set the threshold. I think there may be a lot of threshold to determine this.
Sorry, can you repeat the first?
How to determine the status of the virtual machine and how to set the threshold. Maybe you see LLC or occupancy to determine the status, but what's the threshold of this?
Threshold, okay. In this figure, the threshold for the target virtual machines and other virtual machines, or the threshold for the pool, adequate, or excess?
All of them. How do you set them?
Okay. First, we separate target virtual machines from other virtual machines because we believe some virtual machines are idle. They actually have no actual demand for the ALC space. We evaluate its CPU utilization and VM exits and her CPU stack to evaluate that it is really idle and has no actual demand. And for the target virtual machines, we use Intel CMT, like this kind of technology, and integrate it into the KVM hypervisor to sample the virtual machines ALC occupancy and sum it up for a virtual machine.
Thank you very much.
Okay, let's thank the speaker, and one more time. And our next presentation is by, I'm sorry if I pronounce the name incorrectly, Zhanggai Liu, Z-buffer, zero copy, and metadata-free serialization for fast RPC with scatter-gather reflection.
Okay. Hello everyone, I'm Xiang Liu from Xiamen University. Today I'm going to present our work, Z-buffer, zero copy, and metadata-free serialization for fast RPC with scatter-gather reflection. This work is completed in collaboration with Alibaba Cloud. Okay, first let's see the background of this work. When we build a distributed system today, almost everything is connected through RPC. RPC is everywhere, from microservice to AI infra. In cloud service, RPC handles state synchronization across nodes. At the application layer, it enables different services to cooperate as if they were calling local functions. In AI infra, RPC combined with RDMA provides ultra-low latency communication. Previously, network interface cards offered throughput of 20 gigabytes per second with a round-trip time of about 100 microseconds. At this stage, end-to-end codes were typically dominated by network latency. Now, as NICs scale to 800 gigabytes per second throughput, they can achieve round-trip time of around 2 to 3 microseconds. However, CPU speeds have remained stagnant at 3 to 4 gigahertz, while application can utilize multi-cores to enhance performance. This does not scale linearly. Improving multi-core introduces coordination overhead within the application. Therefore, saving CPU time is important for modern microsecond scale apps. Next, let's take a look at the data path during the RPC process. Suppose we need to transmit 3 buffers. First, we need to serialize the data, which involves converting the data structures in memory into a transport format for communication. During the process, metadata will be constructed to record information for each buffer. This will result in a copy. Then we pass the data to the network stack for processing and transmission, which involves another copy. Although modern network data plans such as DPK and RDMA bypass the kernel and eliminate user-to-kernel space memory copies, serialization overheads related to RPC memory copies cannot be avoided. We conducted an experimental test comparing PPoPP and flat buffers to commonly used serialization libraries. The key point is that serialization reduces achievable throughput by 68%, thereby becoming a performance bottleneck. So how can we avoid serialization copies? One observation is that modern data center network interface cards typically feature scatter-gather. This capability gathers data from multiple non-contiguous memory segments into a single contiguous memory segment, thereby avoiding CPU-based copy. Scatter-gather I/O collects address information and size for each memory segment and passes it to the NIC. Then the NIC will use DMA to coalesce these scatter buffers into a single contiguous block of memory. So, can we use the scatter-gather capability of the NICs to eliminate costly serialization copies? The answer is yes, but this will bring new problems. The first problem is that scatter-gather only moves bytes without understanding object structure, such as field order of sets of types. Therefore, when the receiver receives the message, it does not know how to process it. A simple solution is to build metadata to record the relevant information. However, constructing metadata is also quite expensive, resulting in a performance degradation of about 20%. The second problem is how we can use scatter-gather for programming. there are two options. The first is to write custom serialization code for each data type. The second option is to define schemes and implement a compiler for code generation, similar to protobuf or flat buffers. Regardless of the approach taken, programmability becomes a bottleneck, posing significant challenge for developers and offsetting performance gains. Thus, we propose a new serialization library, ZBuffer, which eliminates CPU memory copy and metadata construction. First, I will introduce the programming model of ZBuffer. The scaled getter structure, SG and SG array, serve as the core abstraction for scaled getter-based serialization. The structure of SG consists of a pointer that points to a memory buffer of its racial address and a record of buffer length. An SG is used to represent a contiguous memory buffer, and an SG array is used to represent multiple non-contiguous memory buffers. To use ZBuffer, developers must define data structure in C++, such as the message structure shown. We provide separate impression for common variable length data types, such as strings and array, using pointer and length to represent and thus adapt to scaled getter. The microprocess fields specifies the order of fields to be serialized. ZBuffer leverages C++ features such as template meta-programming and macros to realize compile time static reflection. First, ZBuffer uses the variadic macro to receive a list of fields, thereby registering the fields and obtaining type information at compile time. This process is implemented through the process fields macro, which expands into a template method process fields and passes the list of fields to the reduce function. Subsequently, variadic templates and requisition are used to expand and process all fields, where X represents the current field and XS represents the remaining fields. This part is implemented by the template function reduce. This recursive template expansion occurs entirely at compile time, generating code that is equivalent to directly invoking each field's processing function in sequence. Finally, type specialization is performed. For different field types, the compiler selects the corresponding template specialization to generate the processing code. ZBuffer does most work at compile time, including type checking and the processing logic specialization highly optimized by the compiler. Now let me illustrate the serialization and the deserialization process of the ZBuffer using an example. We need to transmit a message structure containing 3 fields, 1 integer and 2 strings. Naturally, these 2 strings are implemented using ZBuffer. First, we have a message object, and we need to set the values for its fields. First, we set the ID to 4. Then we set the value 1 to buffer 1. Finally, we set the value 2 to buffer 2. Then ZBuffer will construct the SG array to represent the input message. Use the previously mentioned SG to represent each individual buffer. The packet header includes the transporter header, such as request handler type and function identifier. Note that the message object itself is always placed last, and you will see the purpose of this later. After constructing the SG array, pass it to the network stack. Then the NIC will use the information recorded in the SG array to perform DMA on the corresponding buffers pointed to by each SG, correlating them together. The serialization process does not involve memory copy and metadata construction, just constructing the SG array which is eventually passed to the network stack. Now that we have obtained the buffer and know its size, how can we deserialize it back into the character structure? Fortunately, we know the size and the address of this buffer, and we can also determine the size of message object structure using the size of operator. It is 40 bytes. Remember, we previously placed the message object itself at the end of the buffer. Now we only need to construct the message object within the last 40 bytes of the buffer to execute it. This will serve as the metadata required for our deserialization process. After transmission, the recorded pointer address have become invalid. What we need to do now is fix this pointer to point to the correct address. Next, starting at the start of the receive buffer, we process each field in turn in the same order as it was serialized at. First, set the pointer of field 1 to the starting address. After fixing a pointer, update offset used to locate the next address. Then we can use the starting address and offset to fix point 2. Now we have the correct information. It can be seen that we did not copy or construct any additional metadata. The Z-buffer uses the object itself as metadata, which is constructed when the value is set. The entire process only requires passing buffer descriptors and pointer fix, without requiring the CPU to perform any copying. We just show a simple example. For detailed information on the algorithm, please refer to our paper. Based on Z-buffer, we have also implemented a RPC system which integrates the Z-buffer into the zero-copy transfer path. We have implemented a network stack API that supports receiving SGRA. We have also designed a message format for SGRA to properly organize network packets. And the Doring buffers was designed to mitigate memory copying overhead in scenarios involving multiple packets. The detailed information also can be found in our paper. In the evaluation, we test the serialization performance, end-to-end performance, and real application performance. The first is serialization performance. We compare to PPoPP and flat buffers. Z-buffer eliminates CPU memory copies and has serialization overhead independent of payload size. Compared to Conflex, which also uses get-gather, Z-buffer requires no metadata construction, and Z-buffer is about 7. Then we use flat buffers and PPoPP as the serialization layer on the top of ERPC to conduct end-to-end testing with zRPC. Whether in single packet or multiple packet scenarios, zRPC demonstrates significant advantages. Finally, we integrate zRPC with Raft and the master key value store. For Raft, zRPC reduces 20% in latency. The main takeaway is faster, consistent replication is achievable in commodity internet data centers with zRPC. For mastery, zRPC achieves 61% higher throughput, showing immediate copies for larger values can allow the key value to more effectively use the CPU cache for small values, thus improving performance. To conclude, in this paper, we identified the primary bottleneck in RPC results from the copy overhead introduced by serialization. Therefore, we propose Z-buffer, a zero-copy and metadata-free serialization library based on get-gather reflection. It calls these buffers using Nix get-gather and obtains structured information with static reflection to avoid metadata construction. However, the Z-buffer also has some limitations. It requires the object graph to be a directed acyclic graph, meaning pointer-based cycles are not permitted. It also needs macros for implementation, which may not be the most elegant solution, but may be better in CC'26, which supports reflection. Thanks.
Thank you so much. Okay.
Hi, I'm from Huawei, and I have 2 questions. First one is, as I can remember, you are comparing the buffer with PPoPP, and as I remember, some data types in PPoPP has the format transformation. For example, the variant, they can transfer int to a compact format. So does it also work? It can reduce the data size, so maybe occupy smaller bandwidth of the network. So have you considered this in your design kit? Because as I remember, you cannot do such kind of transformation in the data.
Oh, thanks. Yes, PPoPP use some compression solution to compare its data size.
Yeah, yeah.
But in our work, now we don't have considered the data size comparison solution. We just consider how to eliminate the memory copy in the serialization.
Okay, and also related to PPoPP, as I remember, there are also some more high-level structures like maps and some other data structures. Maybe they are not continue in the memory. Do you consider to support such kind of data type in the buffer?
Yes, like you say data structure like a map.
Yes, for example.
Now the buffer only provide interpretation for basic data types such as string and array or some repetition of these data types. For map or set these data types now we don't support, but in the future we will consider this support.
Okay, thank you. And my second question is about are there some requirement for the hardware? For example, the network card or something.
Okay. Actually, our work needs the hardware. For example, some Unix that support ScaleGuard, but but in modern data centers, most servers has the Unix that support ScaleGuard, such as the Malix Connect 5 or Connect 6 or Connect 7. This Unix support ScaleGuard capability. But we also provide a TCP impression for RPC system that doesn't need this, that don't need the NIC that support the NIC that such as the RDMA NIC, because some like in the Linux you can use the system call like write way or read way. This is perform the same function like the ScaleGuard.
Yeah. Any other questions? Okay.
Thank you for the great talk. I'm Sosuke Scar from the University of Tokyo. And my question is about the portability of this method to other language. Do you think this method can be easily ported to other languages such as Rust or Go language?
Now, our impression is designed for C++, but such as other languages like Rust, they have the same function like the macro to implement such design. Also, we can, yes, actually we just support the C++, but you can expose the C buffer code, use the C API to expose it to other languages. Yes.
Okay, let's thank the speaker one more time.
Thank you.
And our next presentation is by Hysun Kim, Scaling GPU to CPU Migration for Efficient Distributed Execution on CPU Clusters.
Okay, thanks for the introduction. This work is done with Robin Han, who just graduated, but due to visa couldn't come in, so I'm presenting the work. Okay, so the goal of the project is, in today's era, there are so many programs written for GPUs, and then they have the SPN deployment styles. However, the GPUs are not always accessible, and we also noticed that there are so many CPUs in these data centers. So can you use this many number of CPUs? As a proof that we measured these usage patterns in the Georgia Tech space clusters in the last year. The chart shows the waiting time on the CPUs and GPUs. As it shows that GPU's waiting time is so much longer than CPU's time. So the motivation of the work is, can you utilize these CPUs? Now, first of all, can you run the GPU code into CPUs? It turns out that actually there are quite a bit of work already have been done to migrate GPU code to CPUs. However, there's a big difference in architecture style. And GPU architectures are good at running many number of lightweight workload threads, and CPUs are good at running a few number of heavy workload. So to overcome these architecture differences, the traditional methods are grouping these lightweight GPU threads into the CPU thread. What it shows here is there is a work statement A, and then there is a barrier, and a statement B, and this work is run by so many number of threads and so many number of blocks. That's the original GPU code. And this code will be converted to the CPU code. Each of the statement A within the thread is wrapping as a loop, and then entire block is executing as one single CPU thread, and then the work will be divided per barrier. And then this code can be translated by compilers, so that original GPU code in this left side, in the kernel code, will be converted to CPU code, and then the host code is invoking this CPU code and using a OMP parallel for the OpenMP style programming. And we actually published this work, also improved version of this from the just simply naively looping these loops. There are some other techniques you can apply, and that work was published in this previous Micro 2024. However, if you look at NVIDIA's native performance, like for example, A100 provide 19.5 teraflops, then the CPUs that were produced a similar time frame, even though the CPUs have many numbers of CPU cores these days, the aggregate performance is 4.1 teraflops. So single GPU has much more high computation capacities than single CPUs. So then the question that goes, can you run this GPU code into multiple CPU nodes? So what is difference is, instead of running one GPU code into this one CPU node, can you run this into these multiple CPU nodes? What it really means is the previous GPU to CPU code translation was utilizing shared memory models. Because GPU is using a shared memory model, all GPU threads execute the same memory space, and memory consistency is maintained by this OS and GPU hardware implicitly. When you're trying to run this GPU code into the cluster of CPUs, then now we get into the problem that how do you execute this code into distributed memory model space? Because each of the nodes has a separate memory space. And then there is also need to have a network communication to maintain any consistencies or coherences. So by trying to running this GPU code is a cluster of the CPUs, now we're converting these shared memory model programs to distributed memory model programs. There are some existing work running distributed shared memory programs, such as the PGAS. So we're trying to utilize this previous distributed shared memory programs style. But existing DSM solutions are proposed for CPU programs. So CPU programs have multiple data style, typically run in the fewer thread, and CPU programs have many irregular memory accesses. So the style that was developed for supporting these DSMs have provided much more flexibilities to point-to-point communications. However, when you're trying to run this code originally written for the GPUs, running on the CPUs, then because original code has so many threads, now it also has many number of threads. And also more importantly, because original program was written for SPMD style, it naturally has a very regular memory accesses. And then naively applying this P2P communications method to the converted from GPU to CPU code can naturally generate so many fragmented network communications. So when we try to use existing PGAS program models to running a GPU code into CPUs, some code, actually more than half, gets the performance improvement, but some code that degrade performance significantly. This a little bit smaller figure shows that x-axis is increasing number of nodes, and y-axis compared to the baseline, how much performance will improve. The ones that below the 1 means the performance is degraded as we add more number of nodes because the communication cost is so much higher. Whereas the benchmarks that above the 1, they get the benefit of running multiple number of CPUs. So in summary, the existing DSM solutions, it was written for mostly handwritten CPU code and targeting NPMD, and remote accesses are much more infrequent, and access patterns are irregular, and the communication patterns are peer-to-peer. Whereas if we try to convert the GPU code into the CPU, then execution models, SPMD style will preserve, and remote access are very heavy, but access patterns are much more structured. So we use the communication pattern that uses collective communications. So the contribution of our paper is we proposed the first GPU to CPU cluster solutions that we proposed a way to have a low communication execution workflow and also introduce compiler transformations, and then we will also evaluate this work in the multiple CPU clusters. So let me show the example how we perform this work. This is an example, simple vector copy. And then the program version have 5 GPU blocks. To make the example a bit interesting, we make a little bit tweak that blocks from 0 to 3 writes 256 bytes, equal size, but the last block, block 4, writes 176 bytes. So they have a different amount of the write communications. So in the phase 0, we divided so that work. And then before the kernel execution, all CPUs nodes have the same memory copy and have all these same sources. And then in the phase 1, we call the partial block execution stage. The CPU 0 executes block 0 and 1, and CPU 1 executes block 2 and 3. By dividing only the equal amount of work, that both CPU 0 and 1 will have the pretty much similar execution time, the work can be computed similar time that without having any staggered thread. So we don't execute the block 4 at this time, and so that each CPU node writes the same amount of data. So that you can also see that CPU node 0 produces a result for the left side of that buffer, and CPU node 1 produces a result, the right side of that 1. The yellow part indicates the produced values. And then we move to the phase 2. At that moment, we use altogether communication to aggregate all the results. So then after this communication phase, all nodes have identical memory space. And after that, in phase 3, we call callback block execution time. The block 4, which has a very little amount of work left, will be executed by all these CPUs. So then after end of this phase 3, all CPUs have the same memory space and memory data. So one of the key challenges that we have to overcome to design this CPU cluster problem was we want to distribute the work. The CPU writes the same amount of data, so the work can be done in the similar amount of time, and the communication patterns are much more predictable. And because of that, we propose a compile analysis to assign the GPU block CPU that analyze the memory accesses, and then also add auxiliary compiler transformation to guarantee that the work is distributable. And if you might have noticed that, in order to perform this kind of work, the write needs to be much distinctable, because as you show in this figure, the CPU node write into this first half of destination, almost half, and CPU node write in almost half of destinations. Means this write needs to be more distinctable. So the paper discusses how we find this patterns. We call these patterns altogether distributable. So the workload needs to have a distinct write buffer spaces, and only that work can be parallelized with this method. Then question would be how many real-world GPU kernels are migratable? It turns out that 80.53% of evaluated kernels, especially for the most of the AIs, are satisfying these conditions. And HPC applications are satisfying them. So that because of this, we approach these solutions. We evaluated this mechanism in the two different kinds of CPU clusters. One is we call the SIMD focused that can have a 32 nodes and then have 2 times of these Intel processors. And then the other is thread focused that can have only 4 nodes, but each of them has more compute. Both of them are chosen for this architecture that we are comparing the GPUs A100, V100 that are produced in a similar time period. And then, of course, the CPUs have still less teraflops than compared to the GPUs. And then these SIMD-focused and thread-focused architectures are connected with 100 gigabits per second internetwork. And then this shows the scalability result. SIMD-focused clusters and thread-focused clusters. SIMD-focused cluster can increase up to 32 nodes. And then some of the benchmarks really get the benefit most linear. And some of them, we find it the peak point that close to 16 nodes. But most of them reach the performance that linearly scales, almost linear scale up to the 32 node. With thread-focused CPU cluster, we were only able to evaluate up to 4 nodes. And similarly, most of benchmarks get the performance with as we increase nodes. And then the 2 of benchmarks have a slow speed up by having 4 nodes. But it shows that by using this method, that we can reduce the communication overhead and it successfully distribute work so that we can get the benefit by adding more number of these CPU nodes. Now, how much is this performance compared to the native GPUs? We cannot say we get better than GPU. It turns out that we are not better than GPU, but we get 39.4% of A100 GPU performance by having this number of the CPU clusters. So this shows the result with A100, V100, and the SIMD-focused CPUs and the thread-focused CPUs. So even though the native performance was lower in these CPUs, by aggregating those, we were getting almost half of the performance of these GPUs. So the conclusion of the work is that we are attacking the problem running a GPU code in the multiple CPU clusters. And then our key solution is, first, we divide the work equally, and then we execute a partial block. And then after that, we use all-gather communications to make all these CPU nodes have the equal same data in the memory. And then we execute the callback block that couldn't be executed. And then we get this 80.5% of workload can show us the minimum overhead of this scaling effect, and it gets the performance. And then so that the benefit of this work is we can utilize the huge amount of CPU resources in data centers by running this GPU code. Thanks for your time. And this code is open source, so you can download it from this the GitHub link. Yeah, thank you. I'll take any questions.
Thank you. Any questions? Okay.
Hello. This is a very interesting work, and it make good use of the single core performance on CPU, and the modern clusters, GPU clusters, often has the high performance CPU on the GPU clusters. So my question is, if this is possible to make the CPU and GPU to cooperate, and if it is possible, how to handle the different steps to run the tasks on CPU and GPU, such as making synchronization?
Okay, it's a very good question. So we haven't gone to that level, but this work certainly can be done by running a CPU and GPU concurrently, or choosing depending on these resource availabilities. Some kernels can be run on CPUs, and some kernels run on GPUs. And because this work is completely decomposable by the blocks, that we can divide the work, the certain blocks can be run on CPUs, certain blocks can run on the GPUs. And then we can also, if we have a hybrid work, the CPU and GPU, we can apply the same techniques that we can do partial executions, both in CPU, a class of CPUs and GPU, and then we have all-gather communications to make this, everyone has the same memory space, and then running the rest of the table lock. But most of the time, the case is we don't have access to GPU. We have to wait for a longer time. So that's when we get these opportunities. And also, the other time is some of the kernels are relatively short. So that it's actually better to just stay on the CPUs. So that's also another time that we're trying to get this benefit.
Okay, I see. Thank you.
Anyone else? Okay.
Thank you. Kenjo Taro from the University of Tokyo. So very interesting way of thinking. So when people are trying to move from CPU to GPU, you're trying to run GPU code. So the programs written for GPU on CPUs. That's a so refreshing way of thinking. So my question is, so I am first slightly confused by your terminology. So thread focused and SIMD focused. So the question I want to ask is, so it is natural to use both SIMD and threads, and is it what you're doing, or can you clarify what you mean by thread focused and SIMD focused?
This is different kind of architectures. We have a two set of architectures that Intel and AMD architectures, so that we rename instead of calling it.
It's the name of the machine.
It's the name of the machines, but we rename it to emphasize that in the Intel's architecture, each of the nodes is a little bit small, but has more vectors, but can increase more high number of nodes. But the AMD machine that we evaluated was this. So it wasn't really different characterizing the different architecture. It was just trying to show that we evaluate a little bit different kind of CPU architecture.
So either way, you are taking advantage of both SIMD and threads.
Yes, both of them. That's not part of this paper. The previous work already did that. We take advantage of vectorizations, and we also have the thread level parallelisms. And on top of that, the contribution of this paper is on top of that. We also use MPI to expand it. So that's the focus of this paper.
And okay, so you showed the performance comparison between CPU clusters and GPU, but do you have a sense of the performance in terms of the utilization? So how close is it the peak of the machine? So on GPU and CPU?
How close compared to the peak performance? That really depends on the benchmarks.
Sure.
Yes. So,
but if you compare GPU and CPU.
So this chart shows the comparison with the GPUs. So it's with this given evaluations, we get almost 40% of performance of the GPU. That's compared the similar time that was fabricated.
So 40% of the no. So I mean, so when you take a GPU program, which for example happens to be running in 10% efficiency, so compared to the peak performance of GPU, and you take this program to CPU and apply your technology, and then what happens on the utilization?
So utilization, so again, that's the previous works, the papers, the contributions. The utilization is some of the work that we can get to very high utilizations, but some of them are not. That's because of when you convert the GPU code to CPU code, we were able to preserve some locality by doing a loop transformations, but we are not always be able to do it. So then also, some of the code, if it can be vectorized, it gets a great performance. But because of sometimes the compiler is not picking up the vectorizations, then we lose performance significantly. So there is some of the benchmark has a gap, so that if you really compare the code is purely optimized for CPUs, then this method, yes, sometimes you get comparative performance, sometimes honestly we don't get good performance as compared to really optimal for CPUs. But this, again, that was previous papers' work, but that what we did was with the compiler techniques that automatically transfer instead of manually converting or manually writing the code. So that it provides, and then by extending it to multiple clusters, we are trying to catch up the performance.
Thank you. Okay, let's thank the speaker one more time. And our last presentation, but not least, is by Ida. Do I pronounce the name correctly? Ida Lee, right? And yeah, so I want to also mention that the paper is one of the papers with the best paper nominee. And yeah, so the paper is Trojan Horse, Aggregate, and Batch for scaling up sparse direct solvers on GPU clusters.
Hello, everyone. I'm Li Yida from China University of Petroleum. The title of my paper is Trojan Horse, Aggregate, and Batch for scaling up sparse direct solvers on GPU clusters. My report will be divided into 4 parts. The first part is the background. So let's talk about the sparse ILU factorization first. Sparse ILU factorization includes 3 major phases: reordering, symbolic, and numeric factorization. The reordering phase aims to permute the matrix A to reduce fill-in elements. The symbolic factorization phase identifies the structures of sparse matrix L and U. And then the numeric stage determines the value of L and U, which is generally the early stage to compute a large amount of floating point operations. Let's see this figure. This figure shows the time consumption of 3 stages. As you can see, the numeric factorization phase spends the most execution time, on average 97%, and is almost the early phase that scales to a large amount of compute nodes. So, for decades, people accelerate the numeric phase by utilizing the parallelism of hardwares, especially on GPUs. However, there are 2 shortcomings of the current solvers. The first problem is the task dependencies restricts concurrency. There are 3 types of tasks in the sparse ILU factorization, and this figure shows the task dependency of factorizing a 6x6 blocked matrix. Firstly, task 1F starts, and then the 4 triangular solve tasks can be executed depending on the result of task 1F. After this, the Schur complement tasks can be executed, but depending on previous results. The dependencies between tasks are complex in sparse ILU factorization, which restricts concurrency. So, the second problem is single task is too small to saturate a GPU. Existing measures breaks the matrix into small blocks and generate small tasks. For supernodal and multi-frontal measures, the input of each task is generally very small, typically the order of about 10. And for sparse bulky measures, the input of each task is generally bigger, typically on the order of 512, with a sparsity of 0.05 on average. So the small scale of individual tasks limits the effective utilization of GPU's parallelism. So to prepare more tasks for our GPU, we do a conduct. In the numeric factorization stage, some tasks are mutually independent and they can be executed concurrently. We conduct a static analysis on the task DAGs from SuperRLU and PangoRLU, recording the parallel task count. Let's see this volume plot. In the volume plot, the width of each vertical position indicates the count of occurrences of a specific batch size. The height of each volume indicates the maximum parallel task count. Let's take this matrix I highlighted. The highest number of tasks can run in parallel are 1047 and 199 in Super Liu and Pangu Liu. This observation brings the potential to run the task in batch mode. However, just batching them is not an easy thing. At least we should have three considerations. Firstly, we should prepare adequate tasks. And then, we should obey the dependency constraints to ensure the result is correct. Finally, we should consider task priority. So, we will design the aggregate stage with two models called prioritizer and container in the Trojan horse. The second stage, to tackle the second circumstance, we need to selectively run the task in parallel. This figure shows the parallelizable tasks when factorizing a 6x6 sparse matrix. As we can see, the diversity of task combination in each parallelizable task group requires us to think about a mechanism to batch diverse tasks. So each batch is diversity. The batch stage would receive the task on different blocks, tasks of different types, and tasks triggered by different diagonal blocks. So for different tasks in one batch execution, firstly, their kernel may be different, such as task 5F and 8S0. The kernel is different, but they can batched. Secondly, their inputs may be dense or sparse blocks, such as, for example, the task 3T and 8T. The 3T is sparse and 8T is dense, and they can be batched. Finally, they may write the same block. Task 9S0 and 9S1 both compute short update on block 9. Batching them will bring red conflict, therefore need atomic operations. So today we introduce our novel method, Trojan horse, to aggregate and batch small tasks for saturating GPUs. Let's overview the Trojan horse. The Trojan horse focuses on scaling up the execution efficiency of a single GPU and scaling out to multiple GPUs and integrate to distributed servers. There are two stages in the Trojan horse, the aggregate stage and the batch stage. Let's see this figure. Firstly, the aggregate stage receive input tasks to the prioritizer. And the prioritizer model divides them into the higher and lower priority ones. For the higher priority tasks, it was sent to the collector model. And however, the collector model is not full, and the GPU is not saturated because the high priority task is not enough. Therefore, we need a container to contain relatively low priority tasks. Once the collector is not saturated, the low priority tasks will be sent. The collector will fetch the low priority task from the container. When the collector falls, a batch of tasks was sent to the executor. After the executor finished the task, executed the task, they were sent to other processes. So this is the Trojan horse. Firstly, we aggregate a group of tasks, and then it was batched right on GPU. A group of tasks can be batched, can be diversity, different types of kernels, and with atomic. So the two phases of our work is just like a Trojan horse goes into a city. This is why we call it Trojan horse. Let's use an example to illustrate how the Trojan horse works. We prepare an example of factorizing a 6-order block matrix using a solver integrated with the Trojan horse. This is the block matrix. Each number on the block matrix labels a non-zero block. An elimination tree, or DAG, of the numeric factorization phase is shown as in the subfigure B and C. Let's see the subfigure C. The tasks are divided into 5 parts by the diagonal blocks 0 to 4 triggering them. The subfigure D shows the Super Liu, the timeline of Super Liu with 4 processes. Super Liu can batch tasks of the same type, tasks from the same elimination tree level. And for Pangu Liu, it executes tasks based on priority and without batching. For those solvers integrated with Trojan horse, the task they can batch tasks of different blocks, tasks of different types, and tasks triggered by different diagonal blocks. So to implement this, there are 4 function models in the Trojan horse. Let's see the first model, prioritizer. The prioritizer is designed to tag executable tasks and separate them into high and low priority ones. It's to ensure the high priority tasks can be executed earlier. There are 3 phases in the prioritizer. The first step is to receive executable tasks. And, for example, after the task 1F and 4F finish, the task 2T, 3T, 8T, and 16T are available tasks, and they can be batched, and they can be executed. Secondly, to prioritize the executable tasks. And finally, to provide executable tasks for the container and the collector. The second model is container. The container serves as a temporary buffer for tasks with relatively low priority. Tasks in the container do not need to be executed immediately, therefore can be deferred to saturate the GPU when high priority tasks are not enough in later time steps. The third model is the container, the collector. The collector is designed to assemble a group of tasks and dispatch them to the GPU. The count of tasks collected by the collector is dynamically determined according to the peak performance and bandwidth of the GPU. There are 2 phases of the task collecting. The first stage is to receive high priority tasks from the prioritizer. And if not saturated, GPU is not saturated, it fetches tasks from the container, fetch the low priority task. These 2 phases is to ensure that most urgent tasks are considered first. The last model, executor, is designed to provide a flexible batched kernel. It is to let heterogeneous tasks run simultaneously. The heterogeneity of the task is reflected in 3 aspects. Firstly, each task can execute different types of kernels. And secondly, each matrix block can be dense or sparse. And finally, whether or not need to handle red conflicts can be configured. So, to execute multiple tasks in one CUDA kernel, we map tasks to CUDA blocks. When execution, CUDA blocks using their block index to identify their tasks. The final model, the last model is the executor. The executor is to provide a heterogeneous batched kernel. And this is the 4 different types it supports. So let's come to the experiments. Firstly, the experiment setup. We evaluate these solver variants: SuperRLU without and with Trojan horse, Pango RLU without and with Trojan horse, Pango RLU with multiple CUDA streams inside of the executor of the Trojan horse, PAS6 with CPU and MUMS on CPU. We compiled above solvers with 3 major libraries: CUDA on NVIDIA GPUs or ROCm on AMD GPUs, Intel MPI, and OpenBLAS. The evaluation is conducted in 3 parts. The first part is scale-up evaluation on a single GPU, and second part is scale-out evaluation on distributed multiple GPUs, and finally, the comparison with more than CPU. Let's come to the scale-up evaluation. The scale-up evaluation is conducted on RTS 5060 Ti and RTS 5090 GPUs. These 2 GPUs share the same architecture but differ in theoretical performance, enabling about 4 times, enabling an effective scale-up evaluation. The 4 metrics used are from 3 sparse in the scale-up evaluation. We firstly trace the numeric factorization phase of SuperRLU and Pango RLU without and with the Trojan horse. The performance of each kernel execution are shown in these figures. Let's see the matrix lim of Pango RLU as an example. The solvers integrated with Trojan horse has higher average performance and completes factorization faster. This figure shows the scale-up evaluation performance. The following figure illustrates the performance of different solvers on 4 example metrics. Each bar is a comparison of RTS 5090 and 5060 Ti. With Trojan horse, the speed up of SuperRLU is 1.94 times. And for Pangu R-Liu, the speed up is 3.25 times. However, if without the Tolerant House, RTX 5090 Ti compared to 5060 Ti is only 1.09 times for Super R-Liu and only 1.57 times for Pangu R-Liu. So Tolerant House improved the performance gain attained from faster GPU, which means that it can saturate GPU better. We also evaluate the reduction in the kernel count executions. Our aggregate stage reduced the kernel count, providing substantial tasks to batch. For both Super R-Liu and Pangu R-Liu, the number of kernel execution decreased about 2 orders of magnitude. The Tolerant House, we also observed the reduction in kernel runtime of Super R-Liu and Pangu R-Liu with Tolerant House. We observed an average reduction of 97% for Super R-Liu and an average reduction of 77% on Pangu R-Liu. We also scale up. We also do scale up evaluation on 200 metrics to verify generality. Tolerant House yields an average speed up of 5.47 times and up to more than 400 times for Super R-Liu, and about 3 times and more than 5 times for Pangu R-Liu speed up. This comparison is servers with Tolerant House compared to without Tolerant House. Okay, let's come to the scale out evaluation. The hardware configuration is shown below. On 16-card GPU, H100 and MI50. This is the scale out evaluation. Both Super R-Liu and Pangu R-Liu with Tolerant House continue to deliver strong performance gains as number of GPU increase, despite the workload per GPU is reduced. Moreover, we conduct a comparison with CPU servers. As you can see, the memory bandwidth and peak IP64 performance of a GPU are higher than a CPU by about an order of magnitude. However, as shown in the red box, over the past 20 years, sparse DRS measures are far from saturating modern GPUs because of highly independent of small tasks. Sparse DRS measures on GPUs has been slower than CPU measures. As shown in the red box, today, Super R-Liu disk and Pangu R-Liu on GPU with Tolerant House are comparable to or faster than CPU measures. Conclusion. Firstly, we propose Tolerant House strategy to efficiency aggregate and batch tasks. Secondly, we integrate it into Super R-Liu and Pangu R-Liu. Thirdly, we observed obviously better scale up and comparable scale out performance. For 2 decades, since GPU comes out, sparse direct measures can't that saturate GPU because of small tasks and complex dependency. Today, our measures let servers on GPU comparable to CPU. We believe that the more advanced scheduling techniques and faster kernels can further accelerate sparse direct servers on GPUs. Therefore, this work serves only as a starting point and opens a door to a broader renaissance of sparse direct servers on GPUs. Our work is open source. Thank you.
Thank you. Anyone has any questions? Okay.
Hello, I have a question about atomic operations. Have you ever evaluated the overhead of atomic operations? And is there any method to reduce the overhead?
Okay, thank you. It's a good question. To aggregate and batch the tasks, the atomic operations cannot be avoided. So let's see this page. See this page. This page. There are three types of batch, and the finally types is to handle the red conflicts because of the atomic operations. So we have a strategy to avoid the red conflict, and can be switched by the users. If the red conflict avoid is on, once the task 9S0 collected by the collector, the task 9S1 cannot be collected by the collector, and it was sent to the it will be sent to the container, and for later execution. So, however, this strategy may reduce the batchable task count. So, for some machines and some metrics, it may be useful, and for others not. So, this is posed as a switch, can be configured by users. Thank you.
I have a question. So I think your paper mostly focuses on CUDA, but in the evaluation you also show AMD ROCm, right? If I understand correctly. So any specific challenges that you had with ROCm, or like any kind of specific performance characteristics?
May I?
Did you also use AMD GPUs, right?
Yes.
Yes. So any specific kind of interesting findings on ROCm compared to CUDA GPUs, right? So like NVIDIA GPUs.
Okay, it's a good question. Here's the result comparison of H100 and MI50. When we write our codes, the AMD GPU has a wavefront of 64. However, NVIDIA have a wavefront of 32. However, the trends of both the NVIDIA and AMD are similar.
Okay. Thanks. Any other questions? Okay, I think that concludes the session, and we'll take a break and enjoy the lunch.
still a minute before the time, but why don't we get slowly started? I am the Kenjiro Taura from the University of Tokyo, chairing the session of parallel algorithms. So we have 4 exciting talks about parallel algorithms in this session. Okay, the first is about Pyrmont, which is given by Zian Zhang. Okay, so we are strictly speaking 1 minute before, but why don't we get started?
Okay, okay.
If you're ready, you can get started.
Okay. Test, test. So, okay, let's just begin. Thanks for the session chair's introduction to our work first. And good afternoon, everyone. I'm Zhiyuan Zhang from the School of Cyber Science and Technology at Shandong University. Today, I would like to share something about our work, Pyrmont, accelerating end-to-end zero-knowledge proof generation on GPUs for Planck-based protocols. My talk is divided into 4 parts, following the structure of the paper, but easier to understand. Let's begin with the background. First, I would like to briefly introduce what is zero-knowledge proof, as well as ZK snark. Zero-knowledge proof is a method for one party to cryptographically prove to another that they possess knowledge about a piece of information without revealing the actual underlying information. As an example, the prover can prove to the verifier that he knows the original image of a hash function without revealing it to the verifier. ZKP are divided into 2 stages, preprocessing and proof generation. In the preprocessing stage, the system performs 2 tasks. First, it compiles the program or statement to be proven into an arithmetic circuit. This step is commonly known as arithmetization. Second, it instantiates this circuit using the prover's witness, generating the value for each gate. The second task is trusted setup, which generates the public references needed for the proof generation, including some elliptic curve point size and the public key. Before diving into the details of our work, I would like to briefly explain why we choose Planck family protocols, as there are many ZK protocols. Compared to earlier protocols such as Gross, Planck has 3 main advantages. First, Planck supports a universal trusted setup. As I mentioned before, a ZKP protocol typically needs a setup phase to generate parameters, such as the public key. And this process can take months. With Planck, the setup only needs to be done once, and the same parameters can be reused across multiple different applications. Second, Planck offers stronger circuit expressiveness. Compared to Gross, it supports custom gates and lookup tables, which allow complex circuits, such as range check and bitwise operations, to be expressed with fewer constraints. If you listen to another presentation about ZK this morning in HPCA conference, you will get better understanding on this content. Third, Planck is more efficient than Gross in many core ZK apps, such as cryptocurrencies and blockchain. Pyrmont is built on the Planck protocol, which proceeds in 5 rounds. This slide will show the complete computational flow. So round 1 binds the prover to their private input. This is done by encoding the witness into polynomials through number theoretic transform, or so-called NTT and INTT, and then committing to them by MSM. And round 2 binds the circuit variant with essentially the same procedure. Round 3 is used to verify that all the previously constructed polynomials are correct. This is done by computing a polynomial Tx and committing to it. And in round 4, the prover evaluates all the polynomials at a random point chosen by the verifier. Finally, in round 5, the prover needs to prove that the polynomials being evaluated are indeed the ones constructed earlier. Next, I will move on to our motivation and challenges. In this part,
We first analyzed the end-to-end computation breakdown. Many prior works have shown that the prover latency is dominated by multiscalar multiplication, or the so-called MSM computation, and NTT, and have proposed many impressive optimizations. However, we found that beyond MSM and NTT, Planck also introduces additional operators, such as element addition and multiplication, cumulative products, and even polynomial division. Deploying these operators efficiently on GPUs is not trivial. More importantly, our profiling shows that without optimizing this part, the maximum end-to-end speedup is only about 7 times. Beyond the computation challenge, memory pressure is an even bigger issue for the system. The memory footprint of ZKP mainly comes from 3 factors. First, real-world applications often have very large input size, typically on the order of million. Second, ZKP's data has more than 200 speed widths. Third, some operators cause significant data expansion far beyond the original input size. Taking zero-knowledge machine learning as an example, generating a proof for a single GPT-2 inference can require around 1 TB of memory. For a 7 billion llama model, it can go up to about 4 TB. In contrast, even the most powerful GPU today only has 80 gigs of HBM. The third challenge is frequent communication. On one hand, operations that lack GPU implementation forces us to offload data back to the CPU. So as the example in the round 2. On the other hand, to relieve memory pressure, prior work often places only NTT and MSM on the GPU. Both of them incur significant CPU-GPU communication overhead. Our measurements show that for most ZKP operators other than MSM, data transfer is far slower than computation. For element-wise OPs, the gap is more than 50 times. Moreover, some operators alone can exhaust GPU memory, forcing tiling and additional transfers. For example, the low-degree extension can expand the input by 4 times or 8 times. So a single output can require 8 gigs of memory or even more. To address these 3 challenges, Pipeline proposes a fully segmentable GPU operator library, along with a pipeline executor that efficiently has communication. This is an overview of our segmentable GPU library, in which we implemented almost all operators in Planck with different computational types. For element-wise OPs, the implementation is relatively straightforward, but we still apply some system-level optimizations. We implement aggressive kernel fusion on consecutive kernels, which dramatically reduces intermediate variables. In the most aggressive setting, we merge around 20 kernels. Although this would cause register spilling, it can reduce memory usage by at least 20 gigs. For reduction-based operators, such as polynomial evaluation, the implementation difficulty is moderate. And the core idea is the same. We split the computation into subtasks and execute them in parallel on the GPU. We are delegating the final reduction across subtasks to the CPU. This frees up GPU resources to run other heavier kernels. For polynomial division, NTT, and low-degree extension, efficient GPU implementation is challenging due to their computation patterns and memory constraints. We will go into the details next. First, we introduce the design for poly division. The key observation is that in Planck, polynomial division always uses a fixed linear divisor, x sub z, where z is the verified chosen evaluation point. As a result, the quotient coefficients have a very regular structure. In fact, the general form of the quotient term can be written as a weighted exclusive scan. Based on that, our parallelization is straightforward. Each GPU thread handles 2 coefficients by a thread. Across steps, the thread will rising exponentially, and we compute the weight on the fly, so we don't need to pre-store a large table of powers. Besides, to avoid read-write conflicts across steps. We also use a double buffer design. Second, we introduce our CPU-GPU co-design pipeline for segmentable NTT. So in fact, NTT can be executed in a sharded way by the four-step algorithm. The input of size n is reshaped into an I times j matrix. First, an I-point entity is applied to each column. Second, Twiddle factors are applied via element-wise multiplication. Third, a j-point entity is applied to each row. Finally, a transpose restores the correct output order. In the figure, the numbers indicate element order, and the colors indicate the tail partitioning. The four-step NTT enables tailing, but its main bottleneck is memory access efficiency. During both the column NTT and row NTT phases, the access pattern becomes threaded, so it is misaligned with the whole side contiguous layout. As a result, bandwidth utilization is extremely low, and naive fixes, such as directly using CUDA-MEM copy 2D, provide only limited gains under tail size constraints. The 2D copy can read metrics by columns, but it cannot achieve efficient bandwidth unless you read many columns at the same time, which means that the tail is relatively large. Our solution is to pre-arrange the data on the CPU before transfer. This is equivalent to performing an n-size bit reversal permutation. After that, transfer becomes fully contiguous for any tail size, and the per-tail bit reversal inside column entity and row entity is eliminated. In addition, CPU permutations, CPU-GPU transfers, and GPU computation can be overlapped to head communication overhead. So the last design and also the most heavy operator is low-degree extension. So in fact, LDE expands the input by 2 to the lambda power, where lambda depends on circuit complexity and is typically at least 2 or 3. Simply reducing the NTT sharding design would require zero padding, which causes heavy CPU-side memory traffic and extra transfers. Instead, we apply the permutation directly on the original input. This allows running multiplication and NTT directly on the original small sets. And we pre-allocate each tail's output on GPU with all 0, as the output must be expanded. And we map the kernel results to the output buffer with a fixed rule. This also enables a fused multiplication plus NTT kernel and reduces communication by a factor of 2 to the lambda power. Beyond high-performance operators, a system-level pipeline is also designed. We note that across Planck rounds, memory and computer characteristics vary dramatically. For example, round 1 is mostly compute-bound, while round 3 becomes transfer-bound. The key question is how to balance the transfer-compute ratio across rounds without compromising the protocol's security. In fact, this is not trivial, as the original protocol structure cannot be broken because each round produces the randomness needed for the next round, as I showed in the figure's red arrows. So our solution is to decouple rounds with the independent LDE operation. We move padding, permutation, and the column order NTT in LDE to round 1. This allows the high compute intensity MSM to hide LDE's memory access latency. The intermediate results are then stored on the CPU and later transferred back to the GPU in round 3 to finish the remaining steps. Finally is the evaluation. Here are some results for Pyrmont, include segmental operators and end-to-end proof generation. In conclusion, polynomial division, grand product, and polynomial evaluation achieves approximately 140, 36, and 19 times speedup compared to the CPU baseline in ArcWorks, respectively. The entity design only achieves about 2 times speedup compared to the naive implementation using CUDA MEM copy 2D. However, our design significantly reduces the memory requirements. Our entity achieves comparable performance while consuming tens of times less memory than the baseline. In terms of end-to-end performance, Pyrmont achieves speedups of up to nearly 400 times over the CPU baseline and delivers an average 10 times improvement compared with the SOTA GPU implementation. Most importantly, Pyrmont can complete proving under arbitrary memory capacities while still providing usable performance, which was not possible in prior works. So thank you for listening, and any question, please.
So now time for question. So may I ask, so I have zero knowledge about zero knowledge proof, so, so let me ask a dumb question, very basic question. So, so this is obviously a very excellent, well done implementation work compared to the previous work. But I'm just trying to understand what is the key challenges. For example, when you talk about the memory consumption, you talked about making things segmentable. So what is the key challenge addressing this? So making things segmentable.
So our key motivation to tell the data is that in the real-world application that it is impossible to fit all the data into the GPU one time. So you have to plus the GPU cards you use or use the tailing design. So as this work is done in a single GPU, so we use the tailing techniques.
So generally speaking, so things are relatively easily segmentable if the computation is basically a bunch of independent computation.
Yes,
but
yes.
If there's dependencies, for example, in a graph computation, for example, it is not straightforward to.
We also encounter this problem, as I said in this page. So actually, you cannot move the operators across the red arrows, as this is a data dependency in the protocols.
Mm-hmm.
Yeah.
Okay. Anything else? Okay, so if no questions, so let's thank our speaker again. So, who is the second speaker? Okay.
Okay. No.
Can you bring up the display settings?
Yes. No, seems not connected. Why?
Maybe you want to try this dongle, so USB-C.
Okay.
Okay, here it comes. Okay.
Okay.
Okay, the second talk of this session is given by Shu-Hong Huang, right? Okay, go ahead.
Okay, thanks for introduction. Hello everyone, I'm Shu-Hong Huang from Pyrmont School in Tsinghua University. Today I'm glad to present our work, PPoPP, efficiently parallelizing reverse mode auto-differentiation with direct indexing. Let's begin with some background knowledge about reverse mode automatic differentiation. Automatic differentiation, or AD, transforms a program computing some numeric function fx into a new program calculating its derivatives. As shown by the formulas, forward mode AD returns a program PF that computes the Jacobian vector product. In contrast, reverse mode AD returns the program PR that computes the vector Jacobian product. They differentiate complex programs by applying the chain rule step by step, but in different directions, as shown below. Forward mode AD is efficient in cases where there are few inputs and many outputs, while reverse mode AD is efficient for many inputs and few outputs, which make it widely used in deep learning and is therefore our focus. By granularity, AD systems generally fall into two categories. Semi-AD systems, like PyTorch, differentiate programs in the granularity of tensors and operators, and rely on predefined differentiable operators. Thus, they need new operator implementations for efficiency for new workloads. Fully AD systems, like TapeNet and Enzymni, differentiate programs in a granularity of elements and scalar operators, and can handle programs with complex structures. It is easier to apply fully AD systems to new workloads. So we mainly focus on how to efficiently parallelize reverse mode fully AD systems. I'd like to show an example of reverse mode AD. As you can see, the forward mode calculates and restores intermediates, and the backward parse retrieves intermediates for derivative calculation. And the tape is a structure that brings forward and backward. It is used for intermediates, storage, and retrieval. Stack is adopted by some AD systems as their tape for its last-in, first-out property. However, when AD applications are parallelized, this design may harm the parallel performance. We call this the conflict between parallel summation and tape structures. Here is a differentiated program with a stack-based tape, where push and pop are used for storing and retrieving intermediates. After we parallelize the program over axis I, every thread maintains its own stack tape. You may find the concurrent summations through DYDB, which requires atomic operations to ensure correctness, resulting in poor parallel performance. But why not parallelize the backward parse over axis J instead of axis I? You may find that the lethal property of the stack tape becomes an obstacle, as it requires the backward parse executes in the exact reverse order of the forward parse. However, if we replace the stack with some other data structures that can be directly indexed, like a tensor, then we are free to only reschedule the backward parse without modifying the forward parse. We can parallelize the backward parse over axis J instead of axis I. Then the concurrent summations are eliminated. From this example, we have got two insights. First, the forward and backward need different parallelism. Second, AD systems need directly indexed tape to enable independent scheduling of both passes. Let's expand the first insight. By the chain rule, if a variable is read multiple times in the forward pass, it results in a summation of derivatives in the backward pass As shown in the formula below, it is easy to parallelize over index I in the forward parse, but in the backward parse, it is hard. Conversely, a summation in the forward parse vanishes in the backward parse. So we conclude that different parallelisms are required by forward and backward. However, current tapes imposes limitations on decoupled scheduling. They either couple the structures of forward and backward or incurs high overhead, and their limitations are listed below. This brings us to our system, PPoPP, an efficient parallel fully aided framework featuring directly indexed tape. Here is an overview of PPoPP. The main idea is PPoPP adopts a directly indexed tape design implemented as tensors, which decouples the forward and backward parse structures, enabling PPoPP to independently transform and schedule them for optimal parallel performance. And I want to highlight the three components of our system. The first one is the AD transformation path. It transforms the source program into a differentiated program equipped with tensor-based tape. Then, the tape optimizer will apply static bond analysis to reduce tape size. Recomputation is also applied to trade computation for memory. After that, the summation-aware scheduler will schedule forward and backward passes independently for best parallel performance. Now, let's focus on our tensor-based tape design. It seems that we just need to store intermediates into a tensor instead of other tape. And are we done? Here comes our first challenge: how to track and record different versions of a variable. In the example below, the variable t can be written multiple times, even under conditions, and contributes to multiple versions. How can we know when a new version needs to be recorded? To resolve this, PPoPP adopts a versioning by read strategy. The principle is that only when a variable is read, it takes effect to the output. For each read position, a tensor tape is created, and the tensor shape can be inferred from the loop size. Therefore, each version of a variable can be uniquely identified by its read positions and loop indices. This strategy brings another challenge. Some versions recorded are redundant. For example, if there is no write to a variable between its two read positions, then there will be redundant versions recorded, and it causes memory waste and runtime overhead. PPoPP removes redundant versions through static analysis. If there is no write to a variable between two read positions, corresponding tapes are merged. If there is no write to a variable across the loop, tensor tape is shrunk. This process will proceed recursively. The third challenge is some indices may not map to valid versions. For example, in code snips below, indices ij with j less than m does not map to valid versions. To resolve this, PPoPP will group conditions around each read position and use them to infer a tight index bound through simplification and realization during compilation time. These tighter bonds lead to smaller tensor shapes and help us save memory. Recomputation is also adopted. Only interdependent versions of a variable needs to be recomputed altogether, and these versions can be recomputed as a slice of the original tensor tape, which further reduces memory usage. By applying recomputation, PPoPP trades computation time for less memory footprint, better data locality, and less memory access overhead. By adopting a tensor-based tape, backward is decoupled from forward, which allows PPoPP to schedule both passes independently for optimal parallel performance. PPoPP will identify concurrent summations in the backward parts and try to eliminate eliminate them through program transformation and rescheduling. In the simplest case, summations are over the entire parallel loop, and we just need to switch a parallel axis to another to eliminate concurrent summations. For loop-carried summations, PPoPP uses Pluto plus algorithm to transform the program structure and push dependency to inner loops, and the outer independent loops are free to parallelize. However, above transformations are not enough, as there might be summations along different loop axes in the nested loop, and we have to make decisions on how to parallelize them. For example, summation to dydA is along axis J, while summations to dydB is along axis I, and we propose 3 parallel schemes for these cases. First one, the serialized scheme. It only parallelizes independent loops, so it introduces no concurrent summations, but may suffer from insufficient degree of parallelism. The fission scheme splits the loop nest so that each resulting loop contains summations only along the same axis. This approach effectively exposes more independent axes for parallelization. The final scheme is the collaboration scheme, where the summation axes are also parallelized using parallel summation algorithms to expose extra parallelism. This approach achieves the highest degree of parallelism, but incurs one-time overhead introduced by the parallel summation algorithm. A heuristic algorithm is adopted to determine how to apply these schemes. First, PPoPP will try to fission all loop nests until there are enough independent axes to parallelize, or no fission is possible. Then, if the parallelism is still not enough, PPoPP will apply the collaborative scheme to parallelize some summation axes. We evaluated PPoPP on 2 AMD HPCA 7742 CPUs and 1 NVIDIA V100 GPUs. Our work is evaluated in a variety of workloads, including a small benchmark we proposed, cases from AD Bench, and a real-world application, SoftRes, against both semi-AD and fully AD systems, including PyTorch, Anzimni, and FieldShock. As for the overall performance on CPU, our system achieves a 2.80 times speed up over the best baseline on average, and on GPU, our system achieves a 2.06 times speed up over PyTorch, but performs slightly worse than FieldShock. In the ablation study, we progressively apply listed optimizations to our systems, and the performance of each of the differentiated program gradually advances as we apply these optimizations. Regarding memory, PPoPP's peak GPU memory usage is consistently lower than PyTorch and comparable to FieldShock. It verifies the effectiveness of our optimizations on table sites, including redundant version removal, static bond analysis, and recomputation. To conclude, we identified the conflict between parallel summations and tape structures as a major bottleneck in parallelizing AD. Forward and backward of AD applications needs different parallel schemes, but existing tape designs hinder independent transformations and scheduling of the forward and backward. And our solution is PPoPP. The tensor tape enables independent transformations and scheduling of the forward and backward. Static bond analysis and recomputation are adopted to reduce tape size and trade computation for memory. Finally, PPoPP applies summation-aware scheduling to eliminate concatenarize and exploit parallelism of hardware. And our source code is available on GitHub. Thank you for listening. I'll be happy to take any questions.
Any question?
Thank you for a great talk. I'd like to ask a difference between GPU and CPU. I think GPU has a very particular cache hierarchy and may cause several constraints on GPU execution. Do you have any ideas on such kind of constraints specific to GPU? Or don't you think there isn't any so specific limitations on GPU?
Yes, there is difference between GPUs and CPUs. For example, GPU has RAM, so that every thread can access data faster than access data from HBM. So in the computation, recomputation part. So in the recomputation part, here we can only recompute part of the versions as a slice of the tensor tape and store them in SRAM instead of HBM, which can bring us better data locality and less memory access overhead. I hope this can answer your question.
Thank you. It's clear.
Thank you. I've noticed that you conduct all your experiments on the V100 GPU. So have you ever think of taking the PPoPP into newer GPU architecture like 800 or 800 or Blackwell series? Or is there any challenges to extend the PPoPP to this newer architecture? Thank you.
Oh, thank you for your question. Yes. As I just said, PPoPP is a fully AD system that differentiates the program in the granularity of scalar operations. And the V100 just offers a SIMT programming interfaces and allow us to do so. However, newer generations of NVIDIA GPUs, and they have more compressed, and have many new features like async proxy, TMA, and tensor core, which makes them less like a SIMT style. And to achieve good performance on RAM needs dedicated instruction selection and pipeline, which is also a very hot research topic. And we have seen such work like this works like Triton, Kutai, and Taolang, and they are all doing very good job. And I think if we want to support these new hardwares on PPoPP, we may be able, our system maybe need to be extended to support, to differentiate bulk instructions like MMA, and to fully utilize these new features such as TMA, which is orthogonal to our method. But I still think it would be valuable to differentiate a well-optimized program written for new NVIDIA GPUs that utilizes tensor cores and TMA and generate efficient differentiated programs. And I hope this can answer your question.
Anything else? So may I ask a question? So can you show the experimental result again, comparing your, and so especially the comparison to PyTorch. So my so limited knowledge about this field is semi-AD is basically so just operating on the tensor, so big macro type operators, right? And where it fits, it is supposed to be faster than free AD. Although free AD is more general, but tends to be slower than semi-ID, right?
Can you repeat?
So Python, so PyTorch is a semi-ID
Yes.
AD system, right? And free AD is, generally speaking, a more generally applicable, but tends to be slower compared to semi-ID AD system, where it fits, right?
In fact, PyTorch is a semi-AD system, and it requires you to use a lot of operators to make up your programs, and this will come up with some overhead. For example, if you want to add A and B and you want to multiply the result with C, it will be 2 kernels. But in free AD systems, we can express it in one-fold kernel, and free AD systems can differentiate the kernel and produce another backward kernels. But of course, semi-AD systems like PyTorch also adopted some optimizations like torch.compile to fuse these kernels. I think we all agree that it will be efficient to fuse multi-kernels into one.
Okay, so I'm just trying to understand where so your superior performance compared to PyTorch actually come from. So is it basically that, so the operators provided by PyTorch is somewhat not very suitable for these benchmarks, so you have to combine many operators to make it happen?
Yes.
Okay.
All the kernels written in PyDiff is fused into one kernel, but PyTorch cannot do that. I think this is where the speed up come from.
Okay, thank you. Okay, so thank our speaker again.
Okay. Okay.
So the third speaker are speaking about genome computation, and it will be given by Zonghai Zhang. Is that correct?
Yes.
Okay, thank you.
Okay, thank you. Hello, everyone. My name is Zhonghai Zhang, and I'm from Institute of Computing Technology, Chinese Academy of Sciences. I'm here to present our work, Faster and Cheaper, Pushing the Sequence Alignment Throughput with Commercial CPUs. And this is the abstract of our work. In this paper, we present FastAlign, aiming to redefine CPU-based sequence alignment software, and we have achieved our goal. FastAlign is a practical end-to-end sequence alignment tool with faster performance, greater cost effectiveness, and identical outputs. Let's dive into the details. This is the outline of my talk. I present our work in the following 5 parts. First, let's start with a brief overview of genome and sequence alignment. As we all know, the genome contains the ultimate code of life. It carries the genetic instructions for the development, function, growth, and reproduction of all known organisms and many viruses. Today, genomics plays an important role in many fields, such as human variation detection and cancer therapy, rare disease detection, and prenatal diagnosis. It has transformed our approach to life and health. In recent years, the decline rate in genome sequencing costs has surpassed that of Moore's law, thereby promoting exponential growth in genomic data. By 2025, the scale of sequencing data had exceeded the exabyte level, and this motivates us to develop higher performance genetic analysis tools. The JTK best practice workflow is classic and one of the most widely used genetic analysis. It consists of 3 main steps: sequence alignment, post-processing, and variant calling. In this talk, we will focus on sequence alignment, which is also one of the primary bottlenecks in the genomics pipeline. The sequence alignment process mainly has 3 steps. The first step is find seeds. In this step, we search for candidate matching positions through exact matching. As shown in this figure, S1, S2, these are seeds produced in this step. The second step is chain and filter, which involves linking nearby seeds and removing low-quality chains. The third step is extend seeds. In this step, we extend chains from both ends, applying Smith-Waterman algorithm for inexact alignment, and select the highest score as the final result. We generally divide this process into 2 phases, seeding and seed extension phase, and they are the bottlenecks in the process. For sequence alignment, recent work can be divided into 2 types: traditional CPU-based solutions and those leveraging hardware accelerators like GPUs or FPGAs. Download statistics from Bioconda show that the CPU-based BWMAM continues to dominate the field with lower cost despite being less performant, while GPU and FPGA-based optimizations deliver better performance, but they require more expensive hardware platforms. This reality motivates us to develop a solution that is both fast and cost-efficient. To achieve this goal, we face 2 main challenges. The first challenge is the low memory efficiency in the seeding phase. In fact, the seeding process is a memory-bound algorithm. It is primarily based on the FM index algorithm. The data structure is shown in this figure. We will use an example to illustrate why it is memory-bound. For example, to search for the query AG, we need to perform a backward search until we find the matching results. First, the start position and end position are initialized to the full range. We calculate the next position for the first base, G, by this formula. We can see the OCC data in line 0 is accessed. Using the same method, we can get the position, the end position, EP. Then, using the next base A, we continue to calculate the start position and end position in the next step, and we can see the OCC data in line 3 is accessed. Finally, this gives us the matching results. As we can see, processing each base requires accessing non-contiguous memory addresses, which results in a high cache miss rate. And this is why this process is memory-bound. The second challenge is load imbalance in the seed extension phase. It employs the banded Smith-Waterman algorithm, which has a quadratic complexity. The key to optimizing this process lies in effectively utilizing the CPU's SIMD instructions. BWMAM2 implements SIMD using an interquery approach, where each SIMD lane processes a different rate. However, variations in query lengths lead to load imbalance. To address the challenges mentioned above, we implement fast-align, which accelerates both the seeding phase and the seed extension phase. In the seeding phase, we introduced a multi-stage seeding approach to tackle the first challenge. In the seed extension phase, we implement intra-query SIMD and propose 2 additional optimizations. Next, we provide a detailed explanation of the design. First, we analyzed human genetic data and found that the number of exact matches drops rapidly as seed length increases. Beyond a certain length, the average number of exact match nearly drops to 1. Based on this observation, we evaluated the memory efficiency of 3 index strategies in relation to seed length. Leveraging these genetic data characteristics and index algorithm insights, we divided the seeding process into 3 stages, each employing the most memory-efficient index strategy. We will use an example to illustrate this process. First, as shown in the figure, we retrieve sequences of k lengths in the read and use the camera index to obtain the entry point for the next step. Second, we continue the search process using the FM index algorithm described earlier. We create an improved version of this algorithm called FMT index. We will talk about it later. Third, when the matching range reaches the threshold, we fetch the reference sequence at the corresponding position and compare it with the remaining bases to obtain the final match result. We further optimize the FM index data structure and propose the FMT index. As shown in this figure, the traditional FM index only supports querying 1 base at a time. It requires non-contiguous memory access and a large counting scope. In contrast, our FMT index supports 2 base queries, which reduces 50% random memory accesses via TOCC and TBWT, and reduces the counting scope by introducing MOCC. Furthermore, FMT index maintains a low memory footprint. To solve the second challenge in the seed extension phase, we implement interquery SIMD. Compared to interquery, this approach resolves the issue of load imbalance. And we propose 2 ways to address the performance drawback of element-wise operations. The first one is a dynamic pruning strategy along the anti-diagonal direction. This optimization lets in the key observation that BWMIME requires all backtracking path scores greater than 0 when all scores along the path prior to a boundary position are 0. This position can be skipped in the next round. The same logic applies to the upper bound. Therefore, after each round of computation, we can check whether the calculation range can be narrowed, thereby reducing the overall computation load. The second method is called sliding window. This optimization lets in the key observation. Alignment scores are generally non-increasing, rarely exceeding their starting value. We update the maximum position only when a higher score is encountered, and ignore the non-maximum round. This minimizes element-wise reduction for max score position. This is our evaluation methodology. Our evaluation uses public data from NCBI, consisting of both WGS and WES sequencing data. The baselines include all major open-source CPU and GPU solutions. Let's first look at the overall performance. We see a significant improvement over the baselines. FastLine achieves up to 3 times overall performance speedup. For the cost, FastLine delivers a 2 to 5-fold lower cost than the baselines for processing identical data sets. In the seeding phase, we can see our optimization approach proved highly effective, and FastLine achieves the highest memory efficiency among all baselines. In the seed extension phase, our interquery SIMD parallelization achieves stable performance gains on both WES and WGS data, while interquery SIMD performs better on WGS than the WES. And finally, we conclude our talk. In this work, we propose FastLine, an end-to-end cost-efficient solution for sequence alignment, and we open source it at GitHub. Welcome to try it and feel free to open an issue. Thanks for your listening. Welcome any questions or comments.
Question?
Hello, yeah, thanks for the talk. That was quite insightful. I wanted to ask, have you compared your tool's performance with other state-of-the-art sequence alignment tools like LaZi or the LaZi's GPU version, which is KEGAlign? Have you compared with rest of the things as well?
I just, the baselines is selected from the recent years public work and open source. The name LaZi, did I pronunciation right?
Yeah, that's the correct pronunciation. Because that is also sequence alignment.
Is it for third generation or the next generation sequencing data?
That's for all the sequencing data, because that also performs seed, filter, and extend paradigm.
Okay.
Curious to know.
Oh, okay. Thank you for your question, and that is an excellent point. As I said in the earlier part, the JTK best practice is the most widely used in the second generation sequencing data, and the BWMAM-based mapping solution is the fundamental step in this best practice pipeline. So a lot of work has been developed to accelerate it. But the LaZi, I'm sorry, but I never heard of this. And is it open source work or the recent in the recent conference?
Yeah, that is an open source tool, but that has been available since, I think, last 2007.
Okay, maybe I'll try it later. But in my opinion, BWMAM has a very complicated pipeline. Still, there are many other solutions like bowtie, and in the same way to deal with the sequencing data to the mapping phase. But for the DNA second generation sequencing data, BWMAM is still the de facto mapping solution. Maybe we'll talk about it later.
Okay,
thank you.
Thank you.
Anything else? So probably I missed something, but so you initially talked about in the seeding phase that there's a lot of random memory accesses, right?
Yes.
And so I didn't, so it wasn't very clear to me. So if you eliminated the random access?
Yeah, I eliminated the random access by half because despite the hybrid indexing, I also improved the FM index algorithm using FMT. This is the memory layout for FM, the original FM index and our improvement FMT index. You can see in this. You can see in the original memory layout, it just process only one base in a round, but we can process two bases in a round in the continuous memory addresses. But in this original FM index, if you want to process two bases, you have to access two different and non-contiguous memory address. So this may require two accesses of memory, but this is only one access for memory because the data required for processing two bases is located in the near addresses in memory.
Okay, so I'm still not sure if I understand, so I can take it offline, but are you saying that, so even though if you are, even though you are using two bases, so trying to match the two bases at the same time, they are accessing the same location?
Yes, the same memory addresses.
Okay. Anything else? Okay, so let's thank speaker again.
Thank you again.
say it's okay.
Just look at this. Oh, we got a screen there.
Okay. So the last speaker of this session is. So okay. So you are not the first.
I'm sorry.
Okay. So which one? Zia ma'am. So the first author of this talk, so for some reason cannot make it to the conference. So okay, so let's go ahead.
Okay. Hello everyone. I'm Zia. I'm a fourth-year graduate student at UC Riverside, supervised by Yihan Sun and Yan Gu. And I'm glad to introduce our recent work about the PIM-ZD tree, a fast space partitioning indexes leveraging processing in memory. This is joint work with Yiwei, Hongbo, Yan, Guy, Lakshman, Charlie, and Phil. Before we start, as you can see, I'm just a third author, so I have to say that I have limited understanding about the detail of this work. So if you have any well-prepared questions after this talk, I would suggest you to save them in an email to our first author, Yiwei, and he will answer it in time. Okay, now let's start. This talk has 3 parts. First, I will introduce the space partitioning indexes and processing memory, the PIM architectures, and explain why they matter. And next, I will describe how to design space partitioning indexes for PIM system and highlight the key techniques there. And finally, I will present evaluation results on real-world PIM platforms. Okay, let's start with the PIM and the space partitioning indexes. The story begins at spatial data. Spatial data are geometric objects in the real world, which are generally points in low dimensions, such as points in 2 or 3 dimensions in a map. And the spatial data has been widely used in many real-world applications, such as geographic system, computer vision, and robotics. The space partitioning indexes are used to manage spatial data efficiently. They organize points in tree, where each subtree corresponding to a subspace. There are 2 main families of the spatial indexes. The first family is the spatial mid-partitioning, represented by the ZD trees. At each level, the space in the ZD tree is split in half, and each child node represents one of the subspaces. And the second family is the object medium partitioning, represented by the KD trees. The recursive space division is similar in KD trees, but instead of splitting by geometric midpoint, they use an existing data point as a median. Okay, also that space partitioning indexes manage data efficiently. They suffering from the memory wall. That is a high cost of memory access. Their pointer tracing structure incurs large memory latency at each traversal step. And moreover, to maximize throughput, these indexes are often executed in parallel, which further stresses the memory bandwidth and becomes a major bottleneck. So to address this memory wall, architects have proposed the processing in memory, the PIM structure. The key idea is to place compute units near or inside the memory and enable the computation to occur where the data resides. This reduces the data movements and lowers energy consumption and improves the performance. A typical PIM system has 2 sides, a CPU side with multi-core processors and a PIM side with many PIM modules. Each PIM module contains a lightweight core and a local memory, and communicate with the CPU through memory channels. Real-world PIM system includes the UPMEM and Samsung HBM PIM, both with thousands of the PIM units. Okay, next, I will introduce how to use the PIM to resolve the challenges of spatial partitioning indexes. I will introduce our PIM-ZD tree, the first spatial partitioning indexes on real-world PIM system. Okay, how do we deploy space partitioning indexes on PIM? A common approach in previous work is range partitioning. The tree is split into different subtrees, and each subtree is assigned to a different PIM module. So in this example, as we can see, we have 4 different PIM modules, and each color represents 1 PIM unit. So this design reduces data movement since the queries are sent to the P module that holds that subtree, and all accesses are local. However, it's highly vulnerable to skewed queries. Like, if many queries target the same subtree, for example, several KN queries on the same region, as we can see, one P module becomes overloaded, but the other remains ideal. This is not desirable because we want the workloads in different P modules as balanced as possible. Okay. Moreover, this load imbalance will become worse as the system scales to thousands of P modules, which decrease performance dramatically. An alternative is random mapping. Instead of assigning the whole subtree to a P module, each index node is placed on a random P module. And this solves the load imbalance problem. So that even with the skewed KN queries, the tree traversal are spread across all of the P modules, so the workload is balanced. However, this comes at a cost. That is, almost every pointer trace goes to a remote PIM, causing heavy data movements, actually. As a result, the total data traffic is comparable to a non-PIM design. So this highlights a fundamental challenge in the PIM-based indexes design, which is that we cannot achieve both low data movement and high load balance at the same time. Range partitioning and the random mapping each optimize one dimension, but perform poorly on the others. And of course, if we allow infinite space, a trivial solution is to fully replicate the entire indexes on every P modules. But the space explosion makes this impractical. So our goal here is to achieve all three at once. We want low data movement, we want high load balance, and we want low space overhead. Okay. So to do so, we propose a tunable, 3-layer, top-down design for our PIM ZD tree. The key idea is simple, that nodes that are on higher levels of the tree are replicated more times, while lower nodes are shared less. So for example, we can divide the tree structure into 3 layers, L0, L1, and L2. The topmost layer, L0, is a global shared structure. In other words, the entire L0 will be replicated in all P modules. This reduces point tracing in L0, but we will need to bound the space of the L0 because it will be replicated for all of the P modules. You can find more details at how we can do that how we can bound the space of the L0 in our papers. And the bottommost layer, L2, it uses a pure random mapping, where each node is mapped to a random P module with hashing functions. And this design of the, and the design of the middle layer, L1, is non-trivial. And the idea is to combine the benefits of the replication in L0 and random mapping in the L2. Let me illustrate this with a simple L1 subtree. First, each index node is still randomly mapped to a P module. And then, for each map node, we will build a partially replicated cache. That is, we replicate the ancestors and the descendants of every node within L1 on the same P module. For example, the node 4 has 2 children, so we replicate them in the P module where the node 4 is assigned. And the node 4 has 2 ancestors as well, and we replicate them in the P module as well. So these techniques makes the pointer tracing within the neighborhood of a node fully local, and meanwhile keeping the replication overhead bounded. Okay. So with the different replication and data placement scheme in every layer, the PIM ZD tree achieves both load balance and low communications. It's load balanced because the L0 is fully replicated, and L1 and L2 is random mapping. It has low communication because L0 and L1 traverses are local, and remote pointer tracing only occurs in L2. But we can show that we can bound the height of the L2 trees. Okay, this is the main structure of our PIM ZD tree. I will introduce some supplemental techniques to resolve the practical challenges for the PIM ZD tree. Okay, the first challenge is the imbalance of the ZD trees. The ZD tree splits the space evenly at the mid, so the number of the nodes in each subtree can be very unbalanced if the data is not uniformly distributed. So for example, as we can see, the left region, which is red, has much more points than the right region, that is green. And the tree is highly unbalanced. This imbalance makes it hard to partition and place the indexes on PIM efficiently. So to handle the imbalanced tree structure, the PIM-ZD tree defines the top-down layers of nodes based on the subtree size rather than their tree levels. So for example, to decompose these indexes into 3 layers, we can define the L0 nodes as those with subtree size larger than 8, and L1 nodes as those with subtree size larger than 3. So by decomposing them by using the subtree size, we can decompose them into 3 layers as well. So this size-based decomposition adapts naturally to imbalanced trees, meanwhile provides strong theoretical guarantees. We further improve this decomposition with imbalanced aware chunking, which also uses subtree sizes, and you can come to our paper for more details. Good. Now we see that we can resolve the issue of the imbalance of the tree by augmenting the tree size. However, augmenting the tree size brings another problem as well. That is, the high update cost of the tree size during the updates. We know that to maintain the subtree size, each node has to store a counter for its current subtree size. Like any update at the bottom of the index must propagate to the top. And as a result, synchronizing these counters across all replicates in all PIM modules becomes very expensive. So to reduce its update cost, we introduce lazy counters. The key observation is that the counters for subtree size do not need to be perfectly accurate, so that we can delay the propagating of updates to ancestors until a large number of the changes has been made. Like, for example, the bottom levels buffers insertions and propagates to the counter up every 2 insertions. And the next level propagates every 4 updates. And the next level propagates above every 8 updates. So this delayed propagation significantly reduces the amortized update cost. Okay. Finally, I will introduce our evaluation of the PIM-ZD tree on a real-world PIM system. We evaluate on UPMAM, a European PIM startup recently acquired by the Qualcomm. Their PIM system has 2,048 PIM modules on each machine. And each PIM module is a 450 megahertz RISC processor that can run the C codes with 64 megabytes local PIM memory. The PIM-ZD tree is faster in most of the cases, which achieves about 3.5 times to the 18 times speed up in average. And it also saves about 5 times data movements. You can find more details in our paper. One interesting finding is that the scalability with respect to the data sizes, where the PIM-ZD tree maintains stable throughput even the data size grows. But the scalability for other non-PIM designs would slow down as the increase of the data size. This is because that our theoretical design ensures that the main cost of the update or the operations depends on the number of the PIM modules rather than the data size of n. You can find more details in our paper as well. Our paper presents more interesting results, like we show the asymptotic bounds on the space consumption and the dynamic updates, and we also show more experimental results, such as the trade-off between the throughput and the school resistance, and the sensitivity of dimensions and the batch size. Okay, that's all for my talk. Thanks.
Thanks for the great talk. I'm Dongzhe Li from KAIST, and I have mainly 2 questions. My first question is that your baseline is a CPU system.
Yes.
So I wonder that, is there a reason that you did not choose a GPU system to compare with the GPU and the PIM, or is GPU inefficient for these kind of data structures?
Yes, good question. I believe that's for the GPU, a common question. I'm not the GPU expert, but on my understanding is that GPU, you need to avoid the memory misses, like the cache misses, and you want to have high throughput as possible. But for the tree-like structures, every time that you want chasing a pointers of the tree nodes, you got a cache miss, right? And the tree structure is hard to manage into a flat array, so this may not bring you a high throughput. So in our DIs, we only compare our PIM ZD tree with the CPU-based indexes, such as PKD tree and the ZD tree, so we do not compare it with GPU-based implementations.
Okay,
Yeah.
thanks for your question. I have another question. Do I have enough time? Okay, thanks a lot. When you, first of all, I'm not an expert in the KD trees and those kind of trees,
Yes.
but I think when you update the tree, we need a dynamic memory allocation support to,
Yes.
to do the insertion kind of things, and we
Yes.
need a malloc.
Yes.
And as far as I know, UmmEm does not have a dynamic memory allocation support right now, so I wonder how you guys implemented those kind of features.
Okay, good question. For the memory allocations, because I implemented the PKD tree, I know how to do that. We use a open source library, parallel library that's called Pyrlib to manage the parallelism. And Pyrlib provides some built-in functions to allocate the memories. And the idea is that it will pre-allocate a very large memory pools. And every time you need memories, and you just call the let the Parallel nodes, and Parallel will allocate the corresponding memories. And the memory allocation in Parallel is a parallel, can be done in a parallel manner, so you don't need to worry about that. Yeah.
Okay, thanks a lot. Actually, I really worked on UmmEm a lot for computer architecture stuff. And
Okay.
if you're interested, I think we can talk it offline for more
Sure,
details.
of course.
Okay, thanks
of
a
course.
lot.
Yeah.
Anything else? We have a couple of more minutes. Okay, so if not, so let's thank our speaker again. So this is the end of the session, but also before we conclude, there's an announcement about the excursion. So today we have an excursion, which is supposed to start from 8:30, but if you want to go, after the last session of the today, which ends 6:15, immediately go to the front of the convention center. So there's an entrance. So the volunteers will take you to the boat. So just after the last session, just immediately go to the in front of the convention center. Okay. Thank you.
Okay. Good afternoon, everyone. I'm Liang Zhiqiang from Computer Networks
Just wait for 1 minute so that we can be sync up with other sessions. We have like one parallel session, so you just need to wait for 1 minute. Maybe I can introduce you.
Okay.
Okay. The next talk is by Zhikang Liang from Chinese Academy of Science, and that's TAG. So cache-based system for accelerating billion-scale GNN training on multi-GPU platforms. So give it probably 1 minute, and then you can start. Okay, you just wait for 1 minute more as you're a little bit fast. I guess you can start.
Good afternoon, everyone. I'm Liang Zhiqiang from Computer Network Information Center, Chinese Academy of Science. And I'd like to introduce our work, is TAC. It is a cache-based system for accelerating billion-scale GNN training on multi-GPU platform. And I will introduce by 4 parts. And the first is background and motivation. I will introduce the graph neural networks background. Graph structure are the best way to represent relational properties in data, and the ability of data mining has become an important driving force in artificial intelligence. GNN can support applications in many fields, such as social networks, financial risk control, and power system. And here is the motivation of our work. As graphs grow larger, full batch training becomes a severe bottleneck due to high memory usage, communication overhead, and computational cost. So a sampling-based method can greatly alleviate this issue. However, during sampling, high-degree vertices tend to be repeatedly selected, causing a lot of redundant data to be transferred between the host and the device across different mini-batches. So creating a cache buffer in GPU memory can greatly reduce this redundant data transfer. And I will introduce the TAC system. TAC is a cache-based mini-batch GNN training framework. And the picture in the right side is the overview of TAC system. Here are many steps in the overview. The step 1 and the step 2 is the data preprocessing and the cache initialization by the ACI algorithm. And step 3 is transfer the topology and the features from the hard disk to host pin memory. In step 4 to 6, perform neighbor sampling to the vertices, and it could be sampled from cache buffer or pin memory. And next is step 7. Step 7 is format conversion from CGO format to hybrid format. And in step 8, the framework will fetch features from local cache or other GPU's cache. If cache missed, features will be fetched from pin memory. And the last step is perform computation by tensor core. And here is our 3 innovation. Next, I will introduce the affinity-aware cache initialization algorithm, ACI. The ACI algorithm is a 2-stage algorithm, and it implemented through 4 steps. The step 1, pick top k highest degree vertices as hot, and build the hot subgraph. Step 2, partition the hot subgraph by access frequency width, and then map the partition to GPU's cache. Step 3, propagate labels from hot to cold vertices. The cold vertices take labels from the closest hot neighbors after a few rounds. And in step 4, shuffle by label and push all vertices to each GPU's root queue, and then load hot vertices into cache buffers. This solution not only achieves a precise matching between the sampling task and the cache data within each GPU, but also effectively maintains a high global cache hit rate through distribution method. By optimizing cache layout, can greatly reduce communication latency of inter-GPU, and we have built a unified cache where GPUs can access each other's memory through NVLink to improving the efficiency of sampling and feature extraction. And next, I will introduce the hybrid compression format. The motivation of this hybrid format is to leverage cache system to build a cache-aware operator strategy and use separate storage layout and distinct compute policies of hot and cold data. And here picture is the structure of our hybrid format. The row window offset is record the number of TC blocks per row, and the TC offset record the number of non-zeros in each block, and the sparse A to B record the column indices of non-zeros. TC local bit store a bitmap indicating zero and non-zero element within each TC block. And here is the example of hot data, and the cold data has a structure similar to hot data. Based on this hybrid format, we designed the SPM kernel to efficiently perform sparse computation. And additionally, since each batch requires format conversion of the sample data, we also designed a CUDA-core-based parallel format conversion algorithm that can keep the conversion operator overhead in milliseconds. And we reduce GPU memory across format conversion across format conversions in each batch via memory pool to eliminate costly temporary allocations and deallocation. And I will introduce the hierarchical fine-grained pipeline. Our pipeline has 3 layers. The first layer pipeline is use batch N to hide data prefetching for batch N+1. And the second layer pipeline is fine-grained pipeline overlap of batch generation, neighbor sampling, feature fetching, format conversion, and model computation to hide end-to-end latency. And the third layer is schedule BWTH and BWTC on different CUDA streams for parallel execution. We separate the sampling process and the computing process into 2 processes and ascend on different streams. And the next part, I will introduce the evaluation. Here is the evaluation setup. The experiment we evaluate is in this platform. We use NVIDIA H180 GB SXM GPU with NV switch and NV link. And the communication evaluation, we compared with Legion, Paragraph, and GNLab. And in terms of computation evaluate, we compared with TCGN, DTC, FlashSparse, and ACC. And the end-to-end experiment, we compared with DJL UVA, DJL Guardbolt, FastGL and Legend. All experiment we use a large-scale public dataset such as OGB and SNAP, and we use this. And here is the evaluation of reduced communication by optimizing cache layout. Figure 1 illustrates the overall cache hit rate. It matches the SOTA system Legend while minimizing host and device communication as much as possible. And the figure 2 illustrates the local cache hit rate. It improved by up to 78% and 67% over Legend and the paragraph. And figure 3 is the under the different model tips, the cache maintains good performance. And the fan out in different dips is 25, 10, 5, and 5. And here is the computation evaluation. We improved the computation efficiency by hybrid metrics. And compared to the other SOTA operators, L1 and L2 cache hit rate is much higher, and the operator performance is much better. As shown in the table, compared to other kernel method, our kernel considers tensor core acceleration, compressed format, sparsity awareness, and GPU acceleration conversion. And here is the evaluation of end-to-end performance. We use model of graph stage and graph attention. And the experiment setup is a two-layer model, and the hidden dimension is 256. And the first layer use 8 attention heads, and the second layer use 1 attention head. Batch size equals 8,000. And we compared with DGL UV and FastGL and Legend and Garbot. The end-to-end performance improved significantly, and the evaluation showed that efficient hardware collaboration can bring significantly benefits. And by the way, the paragraph does not support the Hopper platform, so we didn't compare. And here is the conclusion. We propose TAG. It is a cache-based mini-batch GN training framework. And we propose ACI. It can effectively reduce the communication latency between GPUs in a unified cache. Besides, we propose hybrid format, adopt independent storage layout and different computing storage for hot and cold data. It can integrate the SPM kernel into mini-batch training through efficient format conversion. And the fine-grained multi-level training pipeline can maximize the hardware resource utilization and the parallelism of the system. Compared to the existing SOTA system, our system can improve 2.8 times improvement in the end-to-end performance. And that's all. Thanks for listening.
Great. Let's thank the speaker. And questions?
Thank you for your insightful talk. Could you clarify how the ACI can reduce the inter-GPU communication use system? Thank you.
Okay. we use the platform. It supports the NVSwitch and the NVLink. So we build a unified cache. It can fetch data from other GPUs. If in the GPU samples, when GPU cache miss, it can be access other GPU's cache buffer to fetch data of topology and features. And SAI can match the sample root data and cache data to reduce the inner GPU communication. Okay, thank you.
Very good. Other questions? So we have time. I can also ask 1-2 questions. So one first question is for me that you choose first the K numbers, yeah? How do you find this K? Can you go to that slide? So the first, I mean, when you're talking about your algorithm, how to find this K?
Okay.
The K. So you were choosing K nodes, yeah? Am I right? Can you go to your next slide?
Next.
Go next. Okay, here. So the first is that how do you define the border between cold and hot?
It's determined by whether the vertices is be cached. We preset a cache ratio, and the system will be cache data by the cache ratio. And if the vertices be cached in the GPU's unified cache buffer, it will be
hot.
Be called
okay.
Hot.
Okay, so and I think somewhere in your algorithm you had to define K nodes, I guess, and then you would do clustering. Can you go? I think it was in the next slide, maybe here somewhere where you were choosing a couple of nodes and you had to define K, or
sorry?
Can you go to next slide? I will find for you. Pick top K highest degree vertex as hot. How do you define the K?
Oh, I know. It is the we preset the cache ratio, and
you have a threshold. It could be from dataset to dataset or model to model different, or what?
Sorry.
So you are saying pick top K highest degree vertex as hot.
Top K is calculated by the cache ratio.
Okay. Do you need to have a threshold?
Threshold?
Yeah. Am I right or not? Did you get? Do you need to define a threshold that above this, or from dataset to dataset, from graph to graph, this K will be different? The K that you pick up, top
yes,
K highest
yes,
degree.
I know. K is calculated by the cache ratio, and it's from the total vertices amount.
Okay. I can catch up later. But can you go to your slides where you show at the end the end-to-end result? Okay, the end-to-end, the last slide, I think, on your evaluation.
Oh, okay, evaluation. The last evaluation.
Okay, can you tell me what this ablation means and how do you calculate? That's end-to-end result, yeah? The figure 1 is end-to-end?
Yes, the figure 1 is end-to-end performance.
Okay. And what was the ablation that you did?
The ablation is baseline is no is no. It is base. It compared with base and base plus ACI, and compared with base and ACI and hybrid, and then add the pipeline.
Okay, that means you are showing that different part of tag, how they improve, how they contribute.
Sorry.
Your approach, it's called TAC, yeah?
TAC, yeah.
Okay, so then what the ablation is doing, that you're showing different parts of your approach, or giving this result, or no? I don't know, what is the base?
Oh, actually, base is legend.
Oh, I see, okay.
Okay.
Okay, now I realize. Okay, thank you. Let's thank the speaker.
Okay, thank you very much.
Yeah. And we go to the last talk of this session. The last talk is called DT Miner. Please go ahead. Data-centric system for efficient temporal motif mining. And that's given by Hu Yimbo from Hanjiang University of Science and Technology. So you can connect now, please, and we are on time. You can start.
Why here can show that? Don't I push this? Good afternoon, everyone. I'm Yinbo Hou from Huazhong University of Science and Technology. Today, I will present our work, DT Miner, a data-centric system designed for efficient temporal motif mining. Let's start with the basics. A temporal graph model intersections as time-stepped edges between vertices. On the left, the three pictures just ground applications, social intersections, impediment logical model, and traffic networks. Now, on the below, the right is the core object. A temporal motif is small, time-ordered angel pattern. A match must satisfy both topological and time linearity. Angels follow the same order at the motif, and all matured androids fall within a time span of at most delta. In the figure, the valid machine satisfies the delta window and the required order. The invalid cases are first elder because the androids exceeded the delta time span, or because the temporal order is violated. So, this is not just a subgraph machine, it's a subgraph machine with temporal constraints. This workload is different from static graph mining. In static graph mining, we usually expand by vertices, and the bottleneck is set operations, like intersections. In temporal motif mining, we expand by androids under time constraints, and the bottleneck becomes searching for feasible androids in the right android range. Most exhausting systems use a task-centric approach. Each task maps the first motif android to a graph android, then grows a DFS search tree. In the tree illustration, the read cycles indicate androids that are revisited across many tasks, and the char marks show candidates rejected by elder topological or temporal constraints. The key issue is many tasks explore overlapping regions, but they do it independently. So we get redundant traversal and scaled data access. This shows up directly in the runtime breakdown. In the static bursts, DRAM access can take a larger of time, about 22.7% up to 88.7%, depending on dataset and motif. So, temporal motif mining is frequently memory bound. Improving locality is not optional, it's the main lever. This slide highlights two inefficiencies. First, redundant traversal. With massive parallel tasks, the same temporal androids can be accessed repeatedly, up to 1,000. Second, vested search. Binary searching over the entire outgoing android set causes many unnecessary operations. The point shows more than 87.63% of binary searches can be vested on edges that will be rejected by constraints. So we vest both the bad variance and cache capacity, exactly the best case for a memory-bound workload. Temporal edges are stored chronologically. Neighbor retrieve for a mature vertex often trigger fragment memory access, and the binary search can aggravate locality. In the LLC mix plot, as we increase concretely executed tasks, the total LLC mix rises sharply. Many parallelism can apply cache pressure if access is independent. Now, the key opportunity. The broad chart shows stronger spatial similarity. Many temporal edges are shared across tasks on average. 75.94% of temporal edges are traversed by at least 6 tasks. At the same time, task traverse edges in strictly chronological order, temporal memoriality. So we can ask, instead of letting each task feature data randomly, can we string edges by time and let many tasks reuse the same cached edges? This does exactly DT miner's main idea. Load temporal edges into cache in chronological order and share them across mature tasks. Reduce redundant traversal and fragment access. We implement the idea with the LES execution model. In the figure, the time-order entry list is partitioned into consecutive chunks loader. We sequentially load one chunk at a time, so each chunk is featured only once. Explore. All tasks that depend on the loaded chunk run in parallel with while it's hot shall catch lights. Second reason, if a task needs entries in the later chunk, we suspend it and resign it when that chunk is loaded, avoiding run across chunk access. That read cross chunk access arrow is exactly what we wanted to control. Designing a real system around the LES model raises three challenges: efficient energy retrieval with each chunk, node balancing underscore temporal graphs, and no overhead synchronization without exploding mental memory. This architecture diagram shows determined structure. We have a locality-aware processor that partitions entries into cache sites, chronological chunks, and building index. Then, a chunk-based exploiter loads chunks sequentially and triggers or relevant tasks to explore them in parallel. Finally, a cross-chunk synchronizer manages task queues, so tasks can pursue and resign across chunks. The key theme is we schedule computation around the data movement, not the other way around. In pre-processing, we build a hierarchy index. The chunk index table records for each vertex its entry range per chunk, and the hash table helps locate the right entry for the scheduled chunk. So when a chunk is loaded, we can quickly answer which entries of the vertex are inside this chunk. At runtime, the key primitive is bound search. Instead of searching a vertex entire entry list, we first locate the vertex entry range inside the current chunk, then binary search only within those bounded to find candidates, satisfying temporal and topological constraints. In the illustration, the effective search regime becomes much narrower than the traditional method, so we reduce unnecessary research and improve cache locality diary exploration. With chunk loading and bound search, exploration becomes cache-friendly. With a loaded chunk, relevant tasks explore in parallel. Record metadata for valid expressions and synchronize only when they truly need the next chunk. But to handle load imbalance, we use three-layer workload stalling: intra-chunk first, then inter-chunk if needed, and also cross-chunk stalling from subsequent chunks already in local memory. This keeps cores busy while preserving locality. Now, cross-chunk synchronization. The diagram shows the workflow. When a task found the next valid candidate entry, it determines the target chunk and anchors the task's metadata into the chunk's task queue. So it resumes and when the chunk is loaded. But metadata consumes memory, so we add memory-aware adaptive synchronizations. We enforce a 30% of total memory by default to keep metadata memory. When the budget is exceeded, the task directly accesses the target chunk for expansion instead of storing more metadata. We evaluate on a survey with two 16-core Xiaolong plant mill, 8,347B CPUs and 503 GB DRAM. We use 4 real temporal graphs and 13 motifs with 3 to 5 entries. The time window delta is set per dataset. We compare with monkey-gun optimizer set of the other CPU temporal motif mining system. Dataset statistics and the 13 motifs are shown in the table and figure. There are the highlight results. In execution time, DT miner achieves 1.14 to 11.98 speed up over monkey-gun across datasets and motifs. On the below, the LLC miss comparison explains the mechanism. DT miner reduced LLC misses by 55.4% to 99.2%. So the gates align with our sensors, better locality and less redundant data movement. We also break down where the gate comes from. Hash index gives improvement about 1.03 to 1.3435. Memory synchronization maintains similar runtime with lower pack memory, and 3 never work stalling is crucial under screw. Compared with the low stalling variant, it adds up to 4.33 to 20 improvement in the evolution view. In scalability, DT miner improves more as standard number increases with 16 floor standards. It reaches up to 52.8 speed up, while monkey-gun reaches up to 25.8. These suggests coordinate trunk-based access scalar better under high concurrency. Finally, end-to-end performance. Even with pre-processing, DT miner achieves about 2.13 end-to-end improvement on average. The cost is additionally pre-processing time, 4.8% and 19.7%, and extra memory, 31.5 to 71.2% for maintaining the hierarchy index. So the trade-off is advancing indexing overhead in exchange for faster multiple mining. To conclude, exhausting temporal multiple mining systems suffer from redundant traversal and fragmented memory access, making them largely memory-bound. DT miner makes mining data-central while LES model, chunk-aware indexing, bound search, synchronization, and NUMA-aware load balancing, and achieved up to 11.98 speed up over a stronger baseline. That's all. Thanks for listening, and I am happy to take questions.
So let's thank the speaker. And questions?
Okay, I want to ask why the speed up is so significantly vary different data sets and patterns.
Okay. It's a very good problem. Let me see you. Okay. It's about this speed up with three level work stalling. Okay. Speed ups vary due to both graph and motif properties. Real-world temporal graph follow power distribution. While some vertices generate many entries with short time window. Motif with multiply entries in the same direction may map to high degree vertices, lead to higher workload for individual standards. Our work stalling strategy is more effective for such imbalanced workload, resulting in a larger speed up for those motifs.
Yes, and I have another technical questions about why do you use the global time-sorted list instead of the per vertex time-sorted list. Okay, thank you.
Do you mean this the figure
yeah.
the figure C?
Yeah. Yes. Why do you use the global time-sorted list instead of the per vertex time-sorted list?
Okay.
Yes, it's the yes edge list.
Yeah. Okay. I mean, I know you mean. Real world temporal graphs are generated chronologically and are commonly stored as time-sorted entry list. Storing few entry data in per vertex and addresses list would duplicate entry information for both endpoints, incurring significant for both endpoints, incurring significant storage overhead. Okay, and therefore, state-of-the-art approach store only Android index in Android list instead of Android list, while maintaining a global time-sorted Android list.
Okay, I think I know.
So other questions? If not, I have very fast question then finish. Okay. So how do you find the optimum number of chunks?
You mean that how I partition the chunk?
Yes. How do you know what is the optimum size of each chunk?
Okay. Yes, the chunk. We use a mathematical to find it. We counted the chunk size, and we counted the temporal data like the metadata of the task and the hierarchy index, and we use the mathematical to find it, and we finally found the L3 cache, the L3 cache, the L3 cache the 1.5 of L3 cache is the better. It is the best.
Mm-hmm. I can catch up also offline. Okay, let's thank the speaker. And as you know now, we have at 6:30 excursion here on Harbor, so you should be there. But we have also one session on optimizing a transformer in 5 minutes. If you are interested, just go, I think, in the other session. But at 6:30 is the excursion. You should be there, on time. Okay, thank you all. And hopefully we see each other again next time. Bye.
And their title is Flash Attention T towards fully tensor attention by exploiting tensor vector parallelism. And welcome.
Good afternoon, everyone. It's my great pleasure to be here at PPoPP. I'm Jianxing Xu from University of the Science and Technology of China, and here we will introduce our work, Flash Attention T towards fully tensorized attention by exploiting tensor vector parallelism. Nowadays, the attention mechanism that captures complex relationship between sequences has become central to modern deep learning. And however, it suffers from quadratic computational complexity with respect to sequence length, making it a frequent performance bottleneck in inference systems. To alleviate this bottleneck, state-of-the-art fused attention implementations such as Flash Attention 2 and 3, consolidated matrix multiplication, and softmax computation into one GPU kernel to improve performance. But in current implementations, these operations remain computationally decoupled. The GEMM leverages high-performance tensor unit, while the softmax executes on slower vector units. This imbalance induces severe vector intervals, periods where the tensor units sit idle, waiting vector unit completion. The vector interval causes underutilization of the tensor unit and also becomes an exacerbating bottleneck within fused attention, along with hardware advancements such as lower precision tensor operation support and faster tensor throughput. To resolve this bottleneck in our work, we propose flash attention T, a fused attention implementation that advances towards fully tensorized attention. Our key insight is to offload critical softmax primitives to the idle tensor unit, maximizing hardware utilization and throughput. Moving to the motivation, we begin by analyzing the algorithmic flow of fused attention. The question here is, within each fused attention iteration, what fraction of time is theoretically spent on softmax commutation? Here we illustrate the common parallelization strategy. Each warp group handles a row block of the output, as you can see in the figure. And within that row block, the commutation is tiled using online softmax, and we accumulate the output over multiple iterations. Diving into the algorithmic flow within each iteration of a warp group, this includes computing the attention logic tile S, updating the logic tile row max, rescaling and exponentiating the logic tile to produce attention score P, summing P's rows, and finally rescaling and accumulating the attention output. This helps us understand where the computational time is allocated. The operation counts for each stage is shown in the table here. Given the effective vector and tensor units throughput, we derive the theoretical softmax time fraction per iteration as listed here. The keys here are that this time fraction amplifies as the tensor to vector throughput ratio increases due to hardware advancements, and is near independent of sequence length. Now to review the vector interval bottleneck, we want to know how much actual iteration time is taken by the vector interval. The flash attention tool optimized for Ampere GPUs uses a scheduling that executes GEMM QK, vector softmax, and GEMM PV sequentially, as you can see here. As the timeline shows, the vector softmax creates a distinct vector interval. Flash attention 3 on Hopper GPUs uses pipeline interwarp group overlapping scheduling as shown here. This scheduling allows some GEMM softmax overlapping, but the non-overlapped softmax still leaves a vector interval. We quantify the vector interval time ratio per iteration by inserting clocking routines into the kernels. The results show that for flash attention 2, the vector interval ratio is around 30%, and it increases to around 36% for flash attention 3 as the GEMM precision drops. These substantial ratios confirm the bottleneck and motivate tensorizing softmax to better utilize the tensor unit. To achieve our goal, we repurpose the tensor matrix multiplier add, or MMA, instructions for executing the key softmax primitives. Those are element-wise multiplication for output rescaling, fused multiplier add for attention logic rescaling, and attention score matrix row summation. Tensor MMA instructions perform GEMMs, D equals AB plus C. So by crafting special B operands, we can adapt these instructions for the operations we just discussed. Modern GPUs partition MMA matrix operands into fragments. Those are vectors of matrix elements in contiguous registers, distributed across cooperative threads like warps. Architecture-specific mapping mu links logical matrix coordinates to fragment elements. Here we show the mapping of an instruction we will be using. For element-wise scaling and fused multiplier add, given scaling factor alpha, we select B fragment values from 0 and alpha so that the MMA instruction yields a permuted scaling between the result fragment D and the input fragment A on the permutation sigma. The permutation sigma here arises from the mapping mu and B choices. We recover the desired unpermuted output with thread local swaps. Since each swap introduces overhead, we minimize the number of swaps required by optimizing the Cayley distance of the permutation sigma subject to the constraint listed here. On the right, we show an optimal B fragment, which implements the permuted scaling here, needing just one swap operation to recover the unpermuted output. And also this optimal B fragment also extends to fused multiply-add repurposing with arbitrary C offsets. For row sum reduction, since the GEMMQK also uses tensor MMA instructions, the tension score matrix P is similarly fragmented. So the goal here is to sum P matrix rows from fragments held by thread quad pairs in each row. The method is that we first reinterpret matrix P's output fragment D as a new input A to the repurposed tensor MMA instruction. This implicitly reorders the row elements into half rows, as we see here, within the new A fragments. Next, using a special B matrix filled with 1 and zeros, these half rows are reduced into a new fragment D. Finally, with two intra-thread add operations, the desired row sum is produced. We now make a brief discussion on the three repurposing we just introduced. First is an important algorithmic constraint. The scaling and FMA repurposing requires a uniform scaling factor alpha across all input matrix rows, particularly for the HMMA instruction. This is 16 rows. Second, the technique is applicable to Ampere and onward GPUs, and it also extends to Hopper GPUs' unique WGMA instructions. In addition, one key strength is that this technique has no memory copy overhead, as everything operates on registers directly. Now for our tensorized online softmax algorithm. While our repurposing enables tensorizing tension logic rescaling and attention score row summation, the problem here is that the attention output rescaling needs a per row scaling factor, derived from the attention logic row max M, but our repurposing requires a uniform alpha, as we just discussed. So as such, to enable tensorized output rescaling, we propose a very straightforward surrogate maximum M hat, calculated as the maximum over an X row tile, including the row of interest. This surrogate enables tensorizing output rescaling as it ensures uniform scaling factor per tile. So this is very straightforward, so we'll mainly cover its numerical stability next. In standard safe online softmax, the running row max M ensures the exponents are always within range of 0 to 1 for stability. A key observation is that the softmax remains numerically stable with any surrogate M as long as, first, no exponent overflows to infinity, so no infinity over infinity error occurs. And also, not all exponents underflow, so there is no 0 over 0 error. For our tile max surrogate, since it's always greater or equal to the true row max, it would strictly ensures no overflow occurs. And the all underflow case is also unlikely with typical Gaussian-like attention distributions, though still possible in worst cases. And we can only fall back to vectorized output rescaling them. But nevertheless, our synthetic and end-to-end evaluations confirm good accuracy and stability. Now with the two techniques we introduced, it's possible to tensorize all compatible softmax primitives as listed. However, preliminary results show an all-tensorized scheme yields marginal gains. The reason is that the repurposed tensor MMA instructions have identical effective throughputs to the vector instructions. Thus, we propose instruction-level parallelism, ILP, and thread-level parallelism, TLP, scheduling that split softmax into tensor and vector portions, then parallelism across the two units for improved softmax throughput. On Ampere GPUs, flash tension 2 cyclically assigns 16 row tiles to warps in a warp group. Based on this tiling scheme, we aim to split each warp's rescaling computation on its tile into tensor and vector portions. Here, possible split strategies include horizontally splitting all of the warp's tiles or cyclically splitting the rescaling on the tiles to be either vectorized or tensorized. In addition, we also implement the 16-row surrogate max using the warp all reduced instruction. We then interleave the instructions for the tensorized and vectorized rescaling computation to orchestrate an ILP softmax execution. For incompatible softmax computation such as row max and also exponentiation, we keep them vectorized. This ILP scheduling reduces the vector interval time and iteration time, and also enhances tensor unit utilization. On Hopper GPU, it is possible to facilitate interrupt group thread level parallelism between the asynchronous WGMA instructions and also the vector instructions. Flash Extension 3 already uses this to overlap the GEMM and softmax commutation, but still leaves a vector interval. Beyond this, we split the softmax commutation at algorithmic stages to offload some of the softmax workload to the tensor unit for improved tensor vector parallelism. The three tensorable stages are as previous. Our choice is to tensorize the attention score matrix P row summation. This is strategic as this first creates a balanced tensor vector workload ratio, and it allows us to circumvent the WGMA serialization issue caused by compiler restrictions. You can check out our paper for more details on this specific compiler restriction. In our final TLP scheduling, the tensorized row summation joins the next iteration's WGMA batch for the QK and PV GEMM, running parallel with other VARP groups' vector instructions. This reduces vector pressure, shrinking the vector interval time and also the iteration time. Now for the evaluation part. Our main results focus on attention throughput. We compare flash attention T against state-of-the-art implementations across 2 Ampere GPUs, A100, and also AJX Orin, 1 Hopper GPU, H100, and also various attention configurations and sequence length settings. The average across sequence lengths per configuration, flash attention T achieves mean speedups of 1.05 to 1.17 times against alternatives like flash infra and Triton. The mean speedups ranges from 1.03 to 1.39 times. In this vector interval evaluation, we measure the vector interval ratio of flash attention T versus baselines. That is the fraction of vector interval time in the iteration time. Main results here are that on Ampere GPUs, the ratios are 1.17 to 2.18 times lower, suggesting a more utilized tensor unit. And on H100, the ratios are down to 2.7%, which is a near optimal result in a sense that the vector interval is nearly eliminated. We also conduct an ablation study on the Ampere GPUs. By comparing the ablation variance, we first see that by integrating the 16-row surrogate max hat, we have a slightly improved performance as our VARP all-reduced implementation is more efficient than existing butterfly reduction found in implementations like Flash Extension 2. Based on this variant, we could see that the all-tensorized variant often degrades performance, as the orange bars here show. Since the repurposed TensorMMA instructions offer the same effective throughput as the vector instructions while incurring extra swap overhead. Finally, the full ILP flash extension T consistently improves performance with the softmax commutation parallelized to both the tensor and vector units. We conduct 2 evaluations to examine flash extension T's numerical stability and accuracy. In the synthetic accuracy evaluation, we sample random attention input Q, K, and V and compute root mean square error, RMSE, against the reference IP64 results. And in the end-to-end generated benchmark accuracy evaluation, we replace the PyTorch flash extension 2 kernels with flash extension T, running real LLMs on end-to-end benchmarks to compare the correctness metrics. Here, the synthetic accuracy evaluation results in the plots show the RMSE of the ablation variance under different random input variances. Flash attention T shows higher RMSE than flash attention 2, but within the same order of magnitude. Ablations reveal that for inputs with low variances, the accuracy loss mainly comes from the TF32 commutation in repurposed TensorMMA instructions. However, our end-to-end tests on human eval and MLU with 6 LLMs shows nearly identical correctness metrics as shown here in the table. This also indicates large outliers are rare in trained LLMs, so the practical accuracy is preserved, demonstrating flash extension T's real-world applicability. Now, finally, we make a brief conclusion of our work. To resolve the vector interval bottleneck stemming from the performance heterogeneity between the tensor and vector units, we propose flash attention T, a step towards fully tensorized diffuse attention. The key insight of our work is to offload critical softmax primitives to the idle tensor unit to improve utilization and also performance. The key methods are tensor MMA-based softmax primitives, tensorized online softmax with surrogate maximum, and tensor vector parallelism scheduling techniques. Extensive evaluations show that flash tension T outperforms state-of-the-art implementations, significantly shrinks the vector interval while preserving practical accuracy. And that's all of our work. Thank you very much for listening. And please feel free to ask me any question. Yes, thank you.
So let's thanks for the speaker. And any question from the audience? So I have a question.
Yeah,
so
please.
because the softmax, such computations are typically memory bound. So what I noticed that you mentioned the repurposing of the softmax, right?
Yeah.
Yeah. What's the overhead?
Pardon?
What's the overhead of the repurposing process?
What
is the overhead?
Oh, yeah.
Yes.
So the main overhead involves the swap operation that I discussed in the slides. That is, when you try to implement those element-wise calculations found in the softmax computation, like element-wise multiplication and also fuse multiply add, the inherent layout constraints and inherent computation order within those tensor core instructions would require you to perform at least one swap to get the actual correct result. So the main overhead comes from that. Yes, and other than that, I think the general overhead is quite negligible. Yes.
I mean, the speed up is not only from the repurposing process, but also from the scheduling?
Yes, the speed ups are mainly from the parallelization of the softmax computation to both the tensor and vector units. Yes, as the ablation study here suggests. Yes. So as you can see, if every possible softmax operation is offloaded to the tensor unit, as the orange bar here shows, the performance is actually not very good. And in fact, sometimes it degrades performance as to the baselines. And if after we parallelize the computation to both the tensor and vector units, there is a significant performance gain.
Oh, so from my understanding is that the repurposing process allows you to reschedule the computations?
It doesn't enforce us to reschedule it. It actually opens up an opportunity for us to schedule it, because with the repurposing, the repurposing makes it possible to offload the softmax operations to the tensor unit. However, please notice it still could be these softmax primitives could still be implemented using vector units. So this actually opens up opportunity for us to offload the softmax computation to both the tensor and vector unit. Right.
Okay. Any other question?
Thank you for the talk. I have one question. I may miss something in the talk, but I wonder, Flash Attention 3 already does some pipeline to overlap softmax and the MetMal. So how your performance gain compared to Flash Attention 3?
Yeah, please wait a sec. Yeah, so frankly speaking, let's see here. Yeah, please wait a sec. Yeah, frankly speaking, so Flash Attention 3 actually does a pretty good job at overlapping the GEMM and the softmax computation at FP16 and FP16 precision. So this is when we actually cannot get, we cannot actually squeeze much performance improvement, like maybe only 3 to 4%. But at like lower precision, like FP8 and FP8 precision, so Flash Attention 3 still exposes this vector interval that needs optimization. Yes.
Okay, thank you.
Any other question?
Do you have an idea what the performance implications on Blackwell might be, and if you would see similar improvements from your technique on that architecture?
Oh, I see. So I think that's a very interesting question, and that's actually a future working direction of our work. So I think, so theoretically and actually conceptually, our technique, that our main technique or our main source is to offload like softmax computation to the tensor unit, and which is also viable on Blackwell GPU. And considering that the Blackwell GPU introduces the new TC generation 05 MME instructions that operates on tensor memory. So I think our key strengths, the key strengths of our technique, which is the repurposing causes no extra memory movement, this can still hold on these Blackwell GPUs. So I think, so theoretically, it could still work, especially considering that the Blackwell GPU has significantly improved the tensor throughput, which would, I think, in theory, cause the vector interval bottleneck to be more severe. But for the actual implementation and like experimenting, I think there is still a lot of work to do.
Sure. Very interesting work. Thanks.
Yeah, thank you.
Okay, because of a time limit, so we're going to the next presentation. And the next presentation is actually the accelerating sparse transformer influence on GPU, but the authors told me they cannot present the paper here, so we'll directly skip it. Next will be meta attention, and let's welcome the speaker. The speaker is from the Shanghai Jiao Tong University. You can connect your device.
Okay. Thank you for the introduction. My name is Feiyang Chen from IPADS Shanghai Jiao Tong University, advised by Professor Haibo Chen, and I'm excited to present our work, Meta Attention, a unified and performant attention framework across hardware backends. This is a joint work between Shanghai Jiao Tong University, Microsoft Research, and Peking University. And today, I will introduce how we address the challenge of creating high-performance attention kernels for diverse attention algorithms on different hardware platforms. Let's start with the background. We have observed a clear trend that as the sequence length grows, attention computation becomes the dominant bottleneck in LLM. It consumes the vast majority of the total computation. So, therefore, optimizing attention is crucial for the end-to-end performance. We also observed that numerous attentions are introduced during the past few years. Different models may use different attention variants, such as multi-head attention, multi-query attention, sliding window attention, linear attention, and etc. And therefore, optimizing all of these attentions becomes a non-trivial and complex task. There are two existing methods to optimize attentions. The first method is to use handcrafted libraries like the previous talk, the flash attention. These libraries rely on handwritten GPU kernels to achieve peak performance. However, libraries are lack of programmability. For example, flash attention only supports softmax attention, but we have other attentions like linear attention, sparse attention, and etc. Another problem is that writing these kernels takes a lot of development effort. It typically takes a domain expert 1 year to optimize the library for a single GPU generation. So the second approach is to use compilers to optimize attention. The compilers take the tensor program as input and automatically compile them into executable code, such as the PyTorch inductor. This method has high programmability because it can take any tensor program as input. However, this approach achieves poor performance compared to hand-optimized library. For example, the PyTorch inductor is 9 times slower than the flash attention. So our insight is that we can use a unified attention abstraction to represent all attentions. As the figure shows, instead of writing one library for one attention variant, we use our meta-attention to optimize the attention uniformly. We take the attention abstraction as input, which can represent all these attention variants, and automatically generate the optimized GPU kernel. The unified attention abstraction is inspired by 2 insights. The first is that every attention mechanism is built around 2 core matrix multiplications. The first is the query multiplies with the keys. This operation calculates the attention scores. The second is the scores multiplies with the values. This produces the final output. For example, for the token 2 in the sequence, its query vector first multiplies with the key vectors 0 to 2 and get an attention score. Then the attention score multiplies with the value vector 0 to 2 and get the output of the token 2. The next insight is that all these attentions can be classified into 2 patterns, parallel pattern or recurrent patterns. According to the metric association law, we can first compute the query multiplies with the key, or first compute the keys multiplies with the values. If we first compute the query multiplies with the keys, we call this a parallel pattern, because tokens can be processed in parallel. Each query independently generates the output. If we first compute the key multiplies with the values, we call this a recurrent pattern. The reason is that the result of the keys multiplies with the values can be cached in a hidden state. As we process the sequence, we build these states incrementally. For example, for each new token I, the output for that token is computed based on the result of the previous step. This forces the computation to proceed token by token recurrently. Here we show some examples of the parallel pattern and recurrent pattern. The softmax attention, sigmoid attention are parallel pattern, and the ResNet, the Mamba2 are the recurrent pattern. So our meta-attention is an attention framework that optimizes this unified attention abstraction. It is designed to be both programmable and performant. For programmability, we provide a unified programming interface that allows users to define various attention mechanisms easily. For performance, we build an automated scheduling engine that takes the attention definitions and the hardware configurations to automatically generate the GPU kernels. Let's start with the programming interface. Our programming interface first takes the attention patterns. Here is the parallel, and then takes the input tensor, query, key, and value. However, the problem here is that except for the basic attention pattern, different attention variables apply different operations between these matrix multiplications. For example, standard attention uses softmax on scores, but other variants might use sigmoid, ReLU, or sparse masking strategies. To solve this, we introduce customizable functions. We allow users to define hook functions on the intermediate tensors, like the attention scores. Users can define any element-wise or reduce operation here, such as masking or scaling. Our framework will take these user-defined Python functions and automatically fuse into the GPU kernel. Another problem is that the shape of attention varies a lot in different attention mechanisms or attentions in the different model sizes. So our approach here is to explicitly take the tensor shape as an input. This input tensor shape will also be used for the next automated scheduling part. So using this programming interface, our programming interface is designed to have high programmability. Now, since we have defined attention algorithms using our programming interface, we need to get the performant execution plan for it. The core problem here is that the execution plan has a vast and unstructured search space. First, different attention mechanisms have different shapes. For example, a standard multi-head attention typically has a head dimension of 256. While DeepSeek MRA has a head dimension of 512. Second, different GPUs have different resource constraints. For example, an NVIDIA Hopper has larger shared memory, whereas an older GPU might have a smaller shared memory. Therefore, one execution plan that works well for one shape on one hardware cannot be moved to another shape on another hardware. Our design is that we formalize the execution plan as attributes of intermediate tensors. We assign 3 attributes to the intermediate tensors. First is the tile shape. This defines how large we block the intermediate tensors for each GPU SM. Larger tile shape typically provide better tensor core utilization and a higher compute-to-memory ratio. But if the tile is too large, it will increase register pressure and cause register spilling, which will destroy the performance. The second attribute is memory location. This determines where the data lives in the memory hierarchy. For example, in global memory, shared memory, or kept in register. The third attribute is the pipeline stage. It determines the buffer depth for asynchronous data loading. Increasing the pipeline stage allows the GPU to overlap memory copy latency with computation, but more stages consumes more shared memory capacity. So now we have defined the execution plan, but the search space of the plan is theoretically infinite. We need to constrain this search space. Therefore, we define a hardware abstraction called device config. It contains 2 attributes. The first is the base tile shape. It is the minimal tile shape that is aligned with the hardware instructions. For example, on NVIDIA Hopper, we set the base tile shape to be 64-16-16 to match the requirements of its WGMMA instruction. The base tile shape constrains the space by only exploring the tile sizes that are multiple of this base shape. The second attribute is the memory capacity. This represents the physical limits of the hardware, such as the size of the registered file and the shared memory. During the search, any plan that requires more memory than physically available will be discarded. After we get the execution plan, how to convert the execution plan into code? Our method is that we wrote some kernel templates in GPU DSL, such as the Taolang or Kutlas, and use the execution plan to instantiate them. This finally gets the performance kernels on the hardware. There are furthermore challenges. For example, how to implement online softmax using our programming interface, and how to efficiently search the plan within the scheduling space. You can refer to our paper for more details. Meta attention supports a variety of attentions, including the softmax attention, the linear attention such as Mamba, the attention with unconventional shapes such as DeepSeek MLA, or attentions with unconventional functions such as sigmoid attention and sparse attention. Meta attention also delivers state-of-the-art performance. It can achieve performance comparable to the hand-optimized libraries like Flash Attention 3. For attentions that are unsupported by the existing libraries, it can achieve up to 10 times speed up compared to PyTorch inductor. Meta attention also achieves portable performance on AMD GPU. Without changing the user code, Meta attention achieves high performance on AMD MI250. Meta attention also reduces development effort and is future-proof. Take the DeepSeek MLA as an example. Users can efficiently implement MLA using our programming interface with 90 lines of Python. To conclude, Meta attention addresses the problem of the explosion of attention variants with diverse hardware by providing a unified framework. It contains a unified programming interface to define attention and an automated scheduling engine to achieve high performance. Our code is open source, and we invite you to try it out. Thank you very much for your time, and I'm happy to take any questions.
So I thank the speaker, and any question?
Thank you for your great talk, and I have a few questions. As I know, Flash Info Library also provides some template so that users can customize the attention, like we can apply rope on the fly, and we can modify the attention score. And as I know, there is another work named Flex Attention. They also support similar customization. And what do you think the advantage of your job over these two?
That's a great question. Flex Attention and Flash Info also support customized function on scores, but they only support the parallel pattern, and they are not. They do not support recurrent pattern attention, such as the linear attention. Yeah.
Okay. One more quick questions. I noticed that you implement Flash MLA in your experiment. Yeah. But as I know, in the pre-fill stage, MLA just do the normal MHA, and they will not do the weight absorb skill. So there's no difference between MLA in the pre-fill stage with normal attention.
Yeah. So our Flash MLA here is for decode, and for prefill we just use the normal multi-head attention.
Okay, thank you for your question. Thank you.
Any other question?
Maybe a follow-up to the first question. So if the main difference to Flex Attention and Flash Info is that recurrent pattern that you support, have you explored whether it's feasible to extend the already existing frameworks to support the recurring pattern rather than developing this new meta attention from scratch?
You are asking if the meta attention can be implemented in Flash Info or Flex Attention?
Yeah, exactly. If you could just extend the existing frameworks to support what you do in meta attention.
I think it is. This is possible. We just need to define another pattern in
flex attention. For example, we define a new pattern called linear and gives this as a parameter to flex attention, and we implement this in the flex attention.
Right.
Yeah.
Okay. So, any other question? So I have a question. Can you go back to the scheduling slide?
Okay. Schedule.
Yeah. No. Next. And yes. So in this slide, it said they'll define the scheduling strategy using the number of registers and the size of the shadow memory and the global memory. Did you take the memory bandwidth into consideration?
Your problem is that is the memory bandwidth in this device config?
Yes.
My answer, the short answer is no, because the device config here is to limit the is to prune all the invalid plans. For example, it uses too much shared memory. It cannot, or it uses too much register, and the performance is destroyed. So for the bandwidth, we do not use this to prune the plan.
Okay, thank you. So I guess it will be the end of today's session, and there will be an excursion at 6:30, and I hope you can enjoy it. So thanks again for the speakers.